to go anywhere. We have one meeting during the APS symposium in person, but also it's available online, so we are not forcing anybody to travel. But we ask people to attend the meeting, and, we'll have votes on things that need to be done. And we like people also to volunteer for other standards development. So currently, IEEE APS Standards Committee has 7 standards. I mentioned 145, a standard definition for antennas that currently is about to be 2025. We have 211, which is definitions for propagation. We have 149, recommended practice for antenna measurements, that I will go more in detail. 356, that is a guide. And notice that some of them says IEEE standards, and some of them said recommended practice, and some of them said guide. And that depends on what level they are. A standard means something that is mandatory. You have to do it that way. You have to define it that way. That's the law. Recommended practice is more of like, if you want to do it correctly, you should do it this way. And guide is like, hey, this is a very loose recommendation on how to do it. And then we have 1502, that was published in 2020. That's recommended practice for radar cross-section test procedures, that I will talk briefly about. 1720-2012, that is currently being reviewed. Hopefully we publish it next year. That is recommended practice for near-field antenna measurements. And then we co-sponsor. There is a standard that was an IEEE and is still an IEEE EMC society standard, but because in antenna measurements we use RF absorber, we decided that we should co-sponsor that standard as well. So that is that 1128, which is recommended practice for RF absorber evaluation. That the one that we're working on is for the range 30 megahertz up to 40 gigahertz. And then we have one standard that is being currently developed, is going to, I think has gone to ADCOM, or no, RevCom, Revision Committee for review, and that's Proposal 2816. And that is recommended practice for computational electromagnetics applied to modeling of simulated antennas. It basically looks at free space, and what it gives is recommendations for using different numerical methods. And the idea is, and you may have seen these, I definitely have seen these, numerical methods tools have become really easy to use. And sometimes the actual engine, what makes the method work, is very invisible to the user. And I have seen a lot of people that they know how to use the software, but they have no idea what they're doing. And they will make horrible mistakes. I mean, mistakes that if I have made those when I was a student, they would have failed me in the class. So this standard, the idea is to put something that gives a frame for people to understand, hey, these are the things that I need to be careful if I'm using this method, and understand. And hopefully it has some samples that you can do and check, hey, I'm getting the right solution that I should be getting from this method. So that's one. We just approved 2 months ago Proposal 3720. This is an IEEE recommended practice for electromagnetic measurements using reverberation chambers. This is for measurement of antennas. There is several standards that deal with reverberation chambers in EMC. 1004, don't remember the dash what, 21. That's immunity using reverberation chambers. RS 103 within MIL standard 461 allows for the use of reverberation chambers. Within the standard for calibration of field probes for EMC, There is use of reverberation chamber for calibration of probes. This one is for measurements of antennas in reverberation chambers. Some of it had to do with measurement of the system of the antenna, so cell phone testing in reverberation chambers, efficiency, and some other methodologies that they use the reverberation chambers, like input impedance measurement. So that is starting. If you are interested in that particular area, let me know and I'll put you in touch with the working group manager. And we're continuously studying. Right now, anechoic range validation for antenna measurements is within the 149 standard. We are thinking on creating a mandatory standard on how to do that test properly. So that's one idea that is there. We're looking about automotive antenna testing, having it as a mandatory standard. Data exchange. The idea is to have a standardized file architecture, if you will, for antenna patterns, so that if I'm using software from my company and I measure a pattern, I export it into that file format, and somebody else that is using a software from some other company can import it and compare it. And similarly for computational methods, you will export your pattern file in that thing. And we're studying it, and we think that there is potential for it, but the problem that we're finding is finding people that understand binary files, because right now pattern files, they will have so much information that you probably have to go to binary files and to like start helping with that. And then other ideas for standards are always welcome. So what is a standard? Keep talking about the standards and I haven't defined it yet. Supposedly I should define things before talking about the standards. The standards are a published document that gives specifications, procedures to design or to maximize the reliability of the materials, products, methods, etc. What is the difference between a standard and a recommended practice? Because as you see, we have a lot of recommended practices. The standards use primarily shall. Is the law. You have to do it this way. That's how it's written. Recommended practices, we are not supposed to do shall. When we send the standard to the revision committee, that's the first thing they do. They do a search to see if you use shall and make sure that you're not using shall incorrectly. And if you're using it, they tell you need to change this. So we should use should. You should do it this way. If you want to do it correctly, you should do it this way. What information goes into a standard or recommended practice? You report the methods, the procedures that are widely accepted in the industry and commonly used. That's important. Because, for example, for this reverberation chamber method, there are some people there that have shown results where you can extract the radiation pattern of an antenna in a reverberation chamber. People have been working on this for over 12 years now. It's an interesting approach, but it's not widely accepted in industry. You don't see people measuring radiation patterns in reverberation chambers. You see that, national labs as a thing. You see some people that they do it because they don't have anything else to do with their time. That's true. My friend at Boeing, Dennis Lewis, was working on that, and he was doing it because to him it was fun. But that shouldn't be on the standard because it's not something that is widely accepted. Now, standards used to be that you will create a standard and every 10 years or so you will get together and say, is this standard fine? And everybody will say, yeah, the standard is fine. Okay, we vote to reaffirm. We will reaffirm the standard. So at some point, the Standards Association said, like, no more. From now on, every 5 years, you need to like check that it's okay, that doesn't need any changes. And for sure, every 10 years, you need to revise it. You need to create a working group, go through the standard, and update it. And one thing that happened, and I will talk more about 149, is that 149, we started revising it, and nothing had changed in 40 years. Think how many things changed just in 10 years. So in 40 years, we have to almost rewrite the entire standard again. That was a lot of work. If you don't revise the standard, it becomes, inert. It's there, but it's no longer acceptable as a standard if it's a mandatory standard. So right now, for example, 1720, that is being under review right now, is in that category because 10 years have passed since the publication. So the standard process starts with an idea. Somebody has an idea. Then they bring it to the standards committee, or within the standards committee, we come up with the idea. We vote on it, we approve it, and the next stage is forming a working group. Prior to forming the working group, there may be a study group. We task a small group to go and study, is this necessary? Are people asking for this standard? So there may be a study group prior to the working group. Once the working group gets together, they have authorization to go and work on the standard. They start like getting people that are experts on the area. They start putting the document together. They draft it. That's the drafting stage. And once you have your draft ready, you go, you pass it through revision, editorial revision of IEEE, and then it goes to ballot. And you put it out there for people that are members of the Standards Association to vote on it. And people will vote on it, people will reject it and put comments, people may approve it. Some people may vote, I abstain, I don't want to give a vote yes or no. And then all those comments, you have to address them. And addressing them doesn't mean like, well, I don't agree with what this guy is saying, so we're going to reject that comment. No, you have to say, we are rejecting this comment for the following reasons. You have to give reasons as to why you're rejecting a comment. For 149, when we went after the first balloting, we have a total of 1,100 comments, and we have to go through every one of those. For 1720, we had, I think, was only like, it was under 200. But still we have, I think, 16 comments that we have to incorporate into the document. So then once you go through those, you put it again for balloting. Two things can happen. You go for a second ballot, and some people may put comments on things that they didn't comment before. If they didn't comment on them before, you can reject the comment on the grounds that, hey, you didn't point this out before. Now, they can be commenting on how you address some comment. And you may have to like go and revise those comments. Now, if you get 70% of vote of approval, the standard is approved. Some working group chairs, they like to like go over and over to like try to like make sure that, hey, yes, let's make the best standard possible. But then you run into the danger of going years, with this game. And I personally don't like it. I think that, especially now that we revise the standards every 5 years and every 10 years, at some point you need to like go and put it out there so that people can start using it. So then, like I said, that will be approval, and then you go into the maintenance. And right now, most of the standards of the IEEE APS are under the maintenance. So let's talk about antenna measurement standards. So here are the standards that are part of the IEEE APS standard committee with 2 eyes. I need to get on Lars about those, and myself because I missed it. So I'm going to talk about, there's some standards over there that deal with measurements. I forgot to highlight in red the radar cross-section. But there is that recommended practice for electromagnetic measuring using reverberation chambers. That will be a measurement standard for antennas. There is the 1720 near-field methods and the 149 recommended practice for antenna measurements. Now, where we sit on the antenna measurement standards, we have the far-field methods, and those are covered under 149, and that deals with outdoor far field, indoor far field, direct far field, and then also what my colleague Lars calls analog transformation. An analog transformation of near to far field, he looks at that as compact range and plane wave generators, which is basically you use an array to create a plane wave, and you put your antenna under test field. Dielectric lenses and metallic lenses like transmit arrays will fall under those. I think those are still far-field methods because you immediately get your far-field result through those. Now, I don't agree calling it an analog transformation because near-field methods with the computation of a Fourier transform to get the far field in the case of planar, they were originally done in the 1960s. But in the 1960s, they were not using computers to do the Fourier transform. They were using operational amplifiers whose transfer function will be the Fourier transform. And you will actually go and gather the data, and the operational amplifier in real time will perform the transformation. That was back in the 1960s. And I was lucky enough to meet Dr. Doran Hess that worked on those systems when he was at Scientific Atlanta. Once computers came aboard, then indeed we have what my friend will call digital transformation. And all those methods will fall under the 1720 standard. Both these standards, the 149 and the 145, have the definition of gain. So the standard 145 has the definition of gain and tells you what gain is, what directivity is. They have this very complex, I guess the thing is not working over there, it is. This very complex diagram over there where you have the different things. In 149, we're more practical people, so we went and we drew an antenna. There is your antenna. There is your input. So here, if you're looking just at the radiated power, that's directivity. If you're looking at the difference between the power going into the antenna and the radiated intensity, that's gain. If you look at the power before it goes into the antenna, the forward power going into the antenna, that is realized gain. Most of us, typically, we measure realized gain. But realized gain is technically not gain, although typically we say the gain is. But technically, we should call it realized gain. .149 has a description on, doing gain measurements, both using the 3-antenna method, the 2-antenna method if they're identical antennas, gain bus substitution. And in the near field standard, we actually have a clause that we have set, the next one, the 2026, that deals with gain determination in spherical acquisition, but we have applied to most of the different methods. So you can use a 2-antenna method, or direct method that we call, 3-antenna method. You can do the pattern integration method, and you can do a gain and efficiency transfer method. And then also you have gain determination in planar acquisition, and so on. So Gain determination is one of the more important things, measurement of gain. So all these standards deal with that. So let's talk about 149. If nothing else, because I spent close to it was over 10 years of my life working on that standard. This was the working group. Jeff Forden, that recently retired from NSIMI, was the chair. Lars Foet was the co-chair. I was secretary. And then Justin Dobbins, we made him an honorary member because he helped a lot. Of those 1,000 comments that we have to address, Justin Dobbins dealt with a plethora of them. And then we had the person that was at the time the chair of the IEEE APS, Vikas Moneborn. That was the working group committee. The initial meeting was in the fall of 2013 at AMTA. And that is important because a lot of these measurement antennas, the activities start at AMTA, which is not an IEEE society, but most of the people doing antenna measurements are members of AMTA. They are concerned about the standards and the definitions on the standards, so they are very active on these committees. So in fall of 2013, we have the first meeting about the fact that, hey, there is a new IEEE rule, and the 149 standard that a lot in the industry refer to is going to be inactive. So we need to work on that. And it was in 2015, also at AMTA in 2015, that we finally approved the PAR document. The PAR document is the document that allows you to work on it. So we got approval in 2015. And we have the first ballot 5 years later in 2020. And we continue the common resolution through 2021, and finally we got the approval from the balloting group. So it got voted yes. We got 70% of the votes in 2021. And RevCom approved the preliminary draft on September 23, 2021, and that meant that the standard was finally approved. And it was published on February 18, 2022. This is the working group membership, and you have basically a who's who in antenna measurements, people from everywhere. You have Dr. Oops, what did I do here? Yeah. Okay. We have Professor Manuel Sierra from the University of Madrid. He disagrees with me. We have Lauren Lecoq as well. We have there Michael Fogel, a lot of you may know him. Steve Nichols that I worked with many years, Dr. Jans van Rensburg, a bunch of people that are very knowledgeable, not only in doing antenna measurements, working on equipment to do antenna measurements, designing equipment to do antenna measurements, but also some of them managing labs. You have, for example, Jeff Way, that was in charge of most of the labs at Northrop Grumman before he retired. And this was the balloting group. And indeed, you see a lot of people from the working group were also in the balloting group. That way you ensure that it gets approved. And you can find the standard over there. The standard is for sale. You have to pay for it, like any other standard. But this is, I think, a very, very good document to have. So I'm going to talk a little bit more about the standard. What is the purpose of the standard? What changes we made since the 1977 version? So the main thing was, the main change we did was on the purpose of the standard. Originally, the standard was a big document. Not that it's not a big document now. It is still a big document. But it went into a lot of descriptions that I think were not needed. I mean, it went into like how to design and build a chart recorder. I mean, few of the people here remember chart recorders, but those were basically plotters that, as the intensity of the field was being measured, they will actually record the pattern on a piece of paper. And, nobody uses those anymore. The other thing is that we couldn't make a standard. We couldn't make a mandatory standard because antennas come in many different types. So how you mandate a standard where your recommendations are better suited for doing directive antennas if you're going to be using omnidirectional antennas. So we needed to make a recommended practice. And the most important thing was to make sure that we gave an idea of how to calculate the uncertainty, because uncertainty is extremely important to any measurement. So the biggest change was moving from, the original IEEE standard procedures for antenna measurements to IEEE recommended practice for antenna measurements. And now, for the entire standard, it is assumed that the antenna under test is passive and linear. That was made out of simplicity. That doesn't mean that the methods cannot be applied to nonlinear antennas. And nowadays, most of the antennas are nonlinear because you have especially phase arrays, and phase arrays having integrated phase shifters, amplifiers, etc. Some of these antennas, if you go to more complex radar antennas, they have receivers incorporated into them with analog to digital. So a lot of the antennas being produced nowadays are indeed nonlinear. So the methods can be used, but in the scope of the standard, we mentioned that it was going to deal with, linear passive antennas. There is one place where we mention about nonlinear antennas, and that is on how to measure gain over temperature. Gain over temperature, and I mean the noise temperature of the antenna. That has to do with the receiving equipment and the preamplifiers that may be part of the antenna. And there we give a recommendation for how to measure that. And that only applies to, nonlinear antennas, technically, but it's there on the standard. We felt that it needed to be there, so we incorporated it into the standard. And actually, this is one of the images from the standard that deals with that gain over temperature. The table of contents, you have the usual overview, normative reference, definitions. These first three clauses of the standard are mandated by the Standard Association. And, they have definitions, specific definitions. So, for example, we define the antenna that you use to measure the other antenna is defined as the range antenna. There was a question, do we call it the source antenna? People that were doing more near fields, they prefer to call it the probe or the probe antenna. At the end, we have a vote internal to the committee, and we decided range antenna. It's the antenna of the range. Then we go into antenna range design, how to design the facility where you're going to measure the antenna, what are the recommended practices for that. Antenna range instrumentation, that was updated. So a lot of the things about how to do a chart recorder and things like that were taken out of the standard. And then, we finally go to clause 7. So up to clause 6 has to do with validation of the site, how to design the site, what instrumentation you need. Finally, clause 7 has to do with radiation patterns. And we get into how to measure far field radiation patterns and different things. Then clause 8, measurement of gain and directivity. Clause 9, polarization. Clause 10, radiation efficiency. That's where we incorporate the reverberation chamber, which now is going to have its own standard. Measurements of impedance, special measurement techniques like scale models, plane wave generators, focusing techniques, near field to far field transformations. We mention it, but we point to the 1720 standard. And then clause 13, uncertainty evaluation. How to evaluate the uncertainty on a measurement. Antenna range operation. What are the proper procedures to run an antenna lab? Like training of your people, temperature recording, things like that. Things that you will have to have. So if you want to have ISO, and I don't remember the guide for like a lab, it's the equivalent of the 9000 ISO, but for like measurement labs. Yeah, that one. If you want that, then this is the kind of like recommended practices to like be able to like get that easily. Electromagnetic radiation hazards. Don't step in front of the antenna when the antenna is on, especially if you want to have kids. Although I can tell you, I did it and I had kids. So I had girls. Most of us RF engineers have girls. And then, you know, there is a lot of additional technical annexes on far-field regions, reciprocity, over-the-air measurements for, like, you know, cell phones. We mentioned a little bit about that. Electrical reference board sighting for, like, making a better alignment, impedance mismatch corrections, and bibliography. The bibliography is extremely extended. There is about, I think, close to 300 entries in the bibliography list. It's a recommended practice, so as I said, it's a good manners and etiquette rather than, you know, the law. We incorporated things that were not originally in the standard. We talk about the workstation, the positioning subsystem, the receive subsystem, and the transmit subsystem, and we describe what typically that equipment it is. We mentioned about compact ranges, which in the 149, 1976 was barely a mention of them. We talk a lot about indoor ranges and RF absorbers. There was a lot of how to design an outdoor range in the 1976 standard. On this one, we put guidelines on how to design and evaluate an indoor range. So we talk both about rectangular indoor ranges, tapered indoor ranges, absorber recommendations, and we have incorporated that in the new 1720. In the old 1720, there was no mention about absorber anywhere. I think only a small paragraph for planar, but nothing for the other methods. So we incorporated information on that. New techniques for evaluating, techniques that are accepted in industry, but everybody knew the free space VSWR for evaluating an anechoic chamber. We now include spectral techniques where you will do a planar scan at the quiet zone and then go to the spectral domain, basically do a Fourier transform, and then go back to the spherical domain, and it will point to you sources of energy that are not coming from your main antenna. So you can identify places in the chamber that are causing problems. So as I said, near field, we mentioned it. It was not mentioned in the original standard. Compact range. There was a discussion whether to have a clause purely on the compact range. We decided to spread information on the compact range among all the clauses. I personally disagree, but the working group has to go with what the majority says. That's what the Standard Association states. So the bulk of the people said, no, we should like spread it around in all the areas. So we did. New methodologies, reverberation chambers specifically for antenna efficiency. So we got people from industry, from national labs, and academia that collaborated on that section on how to use the reverberation chamber for measuring the efficiency of an antenna. The Wheeler's cap that everybody's familiar with, I presume, is still there. We haven't thrown it away. We just added reverberation chamber. And uncertainty, which I think is, to me, is the most important clause. IEEE now tell us that when defining uncertainty, we have to follow the GAM or the ISO guide for uncertainty in measurements. So we basically provide an idea of how to estimate uncertainties. You know, we'll tell you, okay, you need to look at the type of uncertainty that it is, what kind of distribution it has, and based on that, then look at what your confidence level will be. We give an example for a compact range. So there, for example, we have the gain uncertainty, and we have here, for example, some potential sources. So what we did, we asked the people that work on different sections to provide what are the potential sources of uncertainty for each method. And some of them did, some of them did not, but thank God we have a revision coming up, so probably we'll stress more into that. But these are, for example, the sources of uncertainty identifiable on a compact range reflector. And we have here some values estimated for some frequency. This was, I think, up in the X band for gain and also for side lobe. And you'll notice that for gain, some of the things, like for example, let's see here, room scattering, so that's reflections from the chamber. For gain, they are not that important. But for uncertainty of the side lobe, they have a higher level there. And you know, and then you have your standard, and then you get your combined uncertainty, and then you calculate your uncertainty for a given level. So let's jump. Any questions on 149? No? I bored you to death? Oh, one question.
Dennis, I have some problems dealing with impulse radiating antennas. So this is antennas in time domain behavior.
Mm-hmm.
And we have struggled a lot in our community because we lack standards able to characterize antennas either in time domain or using frequency domain techniques to come back to time domain. I wonder whether this is something that the society is looking into.
So the question is on time domain antennas, and if we have a standard for those or is mentioned on the standard. Time domain techniques are mentioned, and broad frequency techniques are mentioning in the standard. There is a clause that talks about them. And there was a push by Dr. Everett Farr when he was a member of the committee to look into time domain measurements, and of course he had all his derivation of the S parameters in the time domain, but he kept being, you know, pushed back on his method. I don't know if I agree with his methodology or not. His presentations that I have seen, they make sense to me. I know him personally, and I was in the committee when he was. But there were some people, especially from academia, no offense, that they were very, very against it. One of them in particular is no longer with us, so I think if it were to come again, I think it will probably get through. Unfortunately, Everett is now retired. I think last time I saw him was 2 years ago. But you know, I can put it up for, like, you know. So 1720, the original standard dates to 2012. It had 40 experts from industry working on it, from industry, academia, government institutions. It was created to complement 149/1979, which didn't mention anything about near field methods, yet near fields are accepted in the industry as a method to do it. And you know, so we needed to create a standard, and it was created. Prior to it expiring in 2022, so it's no longer active, we started the method. We started in 2019. And then two things happened. One thing is most of the people working on this were also working on 149. And then also we had COVID. So those two put it on the back burner. But now finally I think we're very close to get it approved. Contributors to the standard, they are basically the people in the working group right now that are working on it. We have people from NIST, Josh Gordon, academia, Dr. Salazar Serreno from University of Oklahoma. We have people from industry, Pat Pelan, Adam McRabani. We have people from different areas, people from Europe, a lot of people from Europe, a lot of people, some people from Asia, a lot of people from the US. You know, so very, very active. And I put there the people that are actually AMTA members. And as you see again, we have a lot of AMTA members that are in these working groups for IEEE. The main the main volunteers, my friend Lars, myself, Jeff, that now retired and it's difficult to get him on the meetings, and Justin, that is always extremely helpful. Although this time, I think about 70 of the comments were from him. So he's tasked with solving his own comments. So this was the original standard with its clauses. And this is the content of the current draft of the standard. So we updated some of them. Measurement systems, there was actually quite a bit of new material over there because everything on the anechoic range that was not there has been incorporated. So now there are actually guidelines on how to line the range with absorber for the different methods, the planar, the cylindrical, not that the cylindrical is kind of a bastard child between spherical and planar. That's how so like bastard childs, nobody likes them. That's not true. I mean, some bastard childs were given novelty titles by their father, the king, and they became very famous, but they're still known as the bastard child. But, you can design a range for cylindrical using the guidelines for planar and spherical. So that's what we're doing there. And, we have things like gain determination. We have a totally new clause on topics that used to be clause 10, now it's clause 12. And now we have uncertainty, we have to change it. The uncertainty on the original standard was the famous 18-term error approach, which was mainly developed by people out of NIST. As a matter of fact, Dr. Doren Hess, rest in peace, he had the 50-term error, which most of the people in the standard decided that that was way too many. So, NIST reduced it just to 18 terms, which some of them in some cases may have no effect whatsoever. Doren Hess didn't like that, and he voted against the standard. But that was Doren, bless his heart. So now we have to be under the gun, under that guide for uncertainty measurements from ISO. And the 18-term error does not follow the GAM on certain things. And we can get on a long discussion about that. I have heard from some of the people at NIST that develop it, and I agree with them. If you just do a lot of repeated measurements to find the uncertainty using statistical approaches, if it's a systemic error in the system, it may not appear because it's always going to be on the same. So you look at your averages, and yeah, they're all fine. But you're missing that systemic error. So that's what they recommend to do other things. But we work on it and we make some changes to like try to like fit with the old approach, which I think was very good, and still be kind of like under the gun. Where we are, we are right now out of the screen. We're back out here somewhere. That was September. But we are looking at the last comments. Like I said, unfortunately, August, usually nothing happens because everybody in Europe is on vacation. I was on vacation, and I don't live in Europe. And then people are busy also because Justin, for example, is the host of the AMTA symposium, so he's extremely busy with the symposium. And Jeff Fordham is retired from the industry, so it's very difficult to get him. So we slowed down lately, but we're right now just at 16 items that need to be incorporated, and then we can like recirculate it with the balloting group. Hey, here's how we address the comments, here is the new standard, get the new votes, and then hopefully, right now we have all the votes. It's approved, but we need to basically recirculate it because of those comments. So hopefully, sometime in 2026, it will be published and approved. Non-regular scanning techniques. Those of you that are familiar with planar to far field techniques, usually you do planar, you do cylindrical and spherical. That's because we have canonical approaches to like then get the far field from those. There are now other methods that you can do once you measure the field in a non-canonical surface, can be a surface of any shape, be able to like calculate the currents on that surface. And there, what we're doing, we're using those measure near fields at those locations, and then using an inverse method of moments to calculate the currents, magnetic and electric currents, that will give rise to those fields. But that can be in any regular surface. So these non-canonical, non-regular scanning techniques are now in the document. There was a brief discussion about them in one of the annexes prior, but now they're being used. I mean, Roddy and Schwartz, some of the near to far field methods that they use, they're based on that FIAFTA approach that was done by a German university, and they're doing that. They're basically doing an inverse method of moments. Time gating in measurements is treated in the standard now, where we can do measurements over a broad frequency and then turn them to time to like be able to like gate out things. So for example, if you have some article over here, like a metallic plate, you can use your time domain to be able to like eliminate that from your measurement and get the right response. Spatial filtering. So in spherical measurements, you go from the actual domain into the spectral domain. You get your measurements and you turn them into spherical waves. And then those spherical waves will have certain coefficients. And you can then use some techniques of measuring the same antenna at two different locations and be able to eliminate some signals that are not coming from the antenna. You can filter those additional coefficients out and reduce the effects of the chamber, for example. So those are incorporated there. Thermal testing of antennas. We're seeing more of that because people are testing antennas that they're going to send into space, or now, your simple cell phone antennas are now phase arrays that have a lot of electronics, and people in the cell phone industry, they want to know that, hey, this antenna is going to work okay in Buffalo, New York, or it's going to work okay in the desert, and you have to test your antenna on a broad range of temperatures. And of course, not to say if that antenna has to go into space. So approaches to do that with RF transparent radomes. I personally don't think that such thing as RF transparent exists, but that's just me. RF or cover with RF minimizing effects. But you can cool the antenna without cooling the entire chamber, because the entire chamber you cannot cool it. That if you have a compact range, for example, and you were doing these techniques, these are mainly for near field, but that will affect your measurement. And comparison campaigns. How to compare different labs, look at the uncertainties between different ones. That's a thing that is discussed also in the standard, how to set it up. And for example, in Europe, they have done some campaigns of looking at different antennas through different labs all over Europe. The Technical Committee on Antenna Measurements is taking over the measurement campaign that the Standards Committee started. So we have two sets of antennas that we pass around through different labs, and then you send us the data, and that data gets published. And the idea is to use that data in newer versions of the standard, and potentially also use it for the computational standard without mentioning the lab. So we don't mention which lab is which. We just put lab 1, lab 2, lab 3, and here is the measurements, and these are their uncertainties, and look, the uncertainties are overlapping, so everything is fine. Some notes, yes, on 1502, and I will finish here and let, I think maybe we have a coffee break. So 1502 is recommended practice on radar cross-section. It was recently reviewed, well, recently, it's already 5 years. And I was part of the balloting group. I was not in the standard itself, but I did some comments there, mainly on the range design. But it has, of course, the usual definitions and background that you will have on any standard. And then it goes into measurement techniques. What type of ranges can you use to do RCS measurements, outdoor ranges, compact ranges, far field ranges, indoor, outdoor, even taper chambers are mentioned there. And then how to characterize the purity of the plane wave, illuminating the target, clutter and noise reduction, target support, how you support your target. Because your target, typically you want it to be in free space, but if you put it in free space, it will fall. So you need some support. So they talk about pylons, phone columns, pros and cons. I think they may even go over ropes to hold the target. RCS imaging. So once you have all your data, how you create images of what you're seeing. So doing Fourier transforms of that data, both in time and in space. And most important, range documentation, which is all the documentation that you should keep on your range. And that's mainly because there was an internal US standard that was used by mainly by the Air Force for different ranges and different defense contractors to make sure that they have this data available for the contracting officer at the Air Force. That, incidentally, that was the original seed that gave birth to this standard. This standard is mainly based on that. Similarly, the 149 standard was based originally in the Scientific Atlanta Blue Book. And then uncertainty, of course, uncertainty being the thing. That the standard is published, is available, so you can go to the Standards Association, and then I believe what it does, it sends you to the IEEE Explore, and you can purchase the standard from IEEE Explore and download it. And as usually with these standards, you have a very group of people, mainly both from Europe and the US, but you have Jeff Bean from Georgia Tech, Brian Kent, formerly of the Air Force, that did RCS and other things for many years. Some people that have passed away, like Eric Walton, Tapan Sarkar. My boss, Stephen Blaylock, is there. But a narrower group of people. It's not an area as broad as, antenna measurements. And also it's an area where a lot of people that are working there, they don't want to be out in the forefront talking about it, because of the work that they're doing. And with that, any questions? Yes, so that the people online can hear you. Keep it pressed for a few seconds till it turns on.
Alô?
Okay.
Obrigado. You didn't mention measurements for synthetic aperture radar. Where is,
Synthetic aperture radar,
yeah,
so I think a synthetic aperture radar, the measurement will follow in two separate things. One of them will be the IEEE standard on antenna measurements, and also the near field standard, because those will give you the techniques on how to measure the antenna that goes with the radar system. I think all the background signal processing that goes into creating the signal, some of it is mentioned in this standard under the creating the imaging thing. Some of it may be under another society, the Electronic Systems, AES. That's a different society of IEEE, a different technical society. And those deal more with the electronic side and all the post-processing side of the radar. But I will have to check if they have a specific one on techniques of doing the post-processing. I doubt they will publish that, because a lot of those are, trade secrets from manufacturers of synthetic aperture radars. But those will be probably the two sources to look into. Guillermo?
Vince, what about radon measurement? Because we have a standard for aeronautic
Mm-hmm.
to test radon, but for meteorological, for weather, I mean, big radons,
Yeah.
because it's not only the sheet
Yeah.
of the radon. You have all the structure.
So there is a standard for the nose radon, for the weather radar that most aircraft have, that will detect, bad weather in front of them. And that's DO-213. That I was actually in that working group. That depends on RTCA, it's a separate, but for weather radars, for weather antennas, I really don't know if there is a standard. Typically, the methodology will be to measure the antenna without the radon, and then measure it with the radon mount. And that's the methodology that is followed even for the nose radar measurements. And then, of course, military radons for actual, target seeking, they have similar method, but then they look at different angles and different things. But for weather radar, I'm not sure. I'm not sure what. I think the approach that I will follow will be just doing a normal measurement without the radon, and then put the radon on to check what the deviation may be.
But we are talking about antenna of 7-11 meters.
You can still do it with a near field system. A near field system will be able to then, it will be time consuming, but you could do it. I mean, still, some of the aircraft radons, like the Boeing 747, and actually I think the 787, and you may know better, but they have fairly large radons that they are, close to 2 meters in size, and you are measuring at 9 gigahertz. So It is a time consuming, but you can do it in a cylindrical near field setup.
Yeah, MVG has a multi-probe system for that. But my concern is you have a very large radome with sometimes a metallic structure, and you can't perform these measurements inside the lab, and you cannot install a very big scanner outside. Sometimes the radar is in the top of the mountain.
I think you could do it. It will be just a very costly custom approach. But you know, we have definitely done near field methods, near field setups outdoors. We have done them for not for measuring the radon, but for calibrating radars on ships. Once they're mounted on the ship, it basically bolts onto the structure of the ship and does your near field scanning to basically then calibrate the array, the phase array. But I think it could be done for the weather radar. It's just, it will probably need to be a custom system to be able to but I think you could do it. I think you will test it. You will have to do the testing of the antenna first, but keep the probe at the same distance that you will have to keep it when you have the radome, because the radome is going to make the volume larger. And also, your sampling and everything, keep the sampling for the radome. So maybe you do first the measurement with the radome on, and then the measurement with the radome off. So you keep everything in the right location. That will be the approach that I will follow to do it. I know it's not cheap, but that's what I will follow.
Thank you.
Hello, I'm a little curious about the automotive antenna standard that you are looking forward. How mature is that initiative, and what is the main objective of it? Is to support the CISPR standards and ISO standards, or is it a complete different thing?
Yeah, it's mainly for the automotive industry, because there are more and more antennas on vehicles, and people are doing the measurements of antennas on vehicles doing different things. Two things happen. One thing is that originally when car manufacturers start putting antennas on cars and they needed to measure the performance of those antennas, what they did, they went to the EMC people that were doing EMC testing on the vehicle and told them, hey, here, do this. And those people, some of them were doing the measurements in their EMC anechoic chambers over a metal ground. Then slowly some other people said, no, we don't drive on metal roads, so we should have something else. So then Japanese manufacturers, especially because their EMC chambers had a ferrite floor that simulated Earth conditions, they started doing their measurements there. And then there were some people that they were doing outdoor measurements. They just have an outdoor range, and they'll have the car on actual concrete or asphalt. So there is not a standardized way of testing those. Each manufacturer has a different one. The Chinese manufacturers are the ones that are putting the most amount of money on standardizing, and they prefer to their technique is to do a near field measurement on the vehicle in a free space condition, or as close as free space as they can have it. And then once you do the near field measurement and you can calculate the currents on a surface that encompasses the car, then numerically you can take those currents to a piece of software and then put whatever kind of ground you want. You can put concrete, you can put dirt, you can put metal, and recreate the radiation in far field. There is going to be some uncertainty, some error, but, you know, as long as you know what that error and that uncertainty is, that's the approach. And that's what I've seen with some of the manufacturers in Asia. That's what the industry, the antenna measurement instruments industry is following. So I know my competitors at MVG are looking into that. I had a paper last year at AMTA on that, where we show our technique for like getting the currents around the antenna in free space and then putting it over different grounds and getting the solution. So the idea with that standard was to like basically put the recommended practice for doing it. And depending on where you're going to do it, what will be the best approach. And things, for example, like collision avoidance radars that operate at 70 gigahertz. The idea was for those, it's like, don't try to like do an acquisition over the entire sphere that encompasses the car, because that, at those frequencies, the amount of the degrees and the amount of points is just outrageous. So they say for those cases, just do a planar scan in front of that antenna, you know, mounted to like get what the image, what the pattern will be. So those were the ideas. Like all these ideas, they come out of a book. So there was a book in Artec House, edited by Manuel Sierra and Lars Foed, on, you know, measurement techniques for vehicles, antennas on vehicles. And the idea was to turn that into a standard, but it haven't yet moved forward. It's like they talk and they haven't voted to like move forward with it. I don't know any of the, like the Society of Automotive Engineers, SAE, I don't know that they have pushed forward for having a standard on that. Like I said, the most active are the Chinese manufacturers to come up with a standardized method. And they're the ones that are putting the biggest chambers right now for like automotive immunity, automotive antenna measurements. But if you go around through manufacturers, you find metal ground planes, simulated earth ferrite floors. You find some that have like, they elevate the vehicle over an absorber, fully covered absorber, and they do the measurement. So everybody's doing a different thing. So that was the idea of like coming up with that standard. At least a recommended practice. Not mandatory, but a recommended practice. Shall we break for coffee? Okay. Well, we're going to, thank you. For those online, we're going to break for coffee here, and we'll be back in 10 minutes, I guess. 15? 15 minutes. So, 15 minutos. Pueden ir ao bañeiro a tomar café. Voltamos en 15 minutos.
So thank you very much for being here for this second part of the workshop today. There is a small announcement to do, is that after my talk there will be lunch served outside. So please just help yourselves outside and wait for the third talk that will also be given by Vince. I'd like to first giving special thanks to Daniel and to Vince for organizing this workshop. I was contacted by Janet O'Neill from IEEE EMC Society asking me to be here, to support the workshop, especially I think it's very important for us countries in the Region 9 to be working together, and I think it's just a matter of setting up schedules and being able to come. So thank you very much, Daniel and Vince, for setting this up, and to Professor Carlos Sartori for hosting us. So before coming, Janet gave me a special mission, is to advertise our coming symposium. So this is EMC's SIPI Congress that is taking place in August 3 to 7 in Dallas. I see a gentleman here with a t-shirt from our past symposium, so this is the next version of it. These are some of the special topic areas that we'll be covering. As usual, we have the EMC subjects, but some special topics this year will be biomedical devices. We're starting to look into microgrids and EMI, EMC issues for transportation in electrification. Well, the WPT problems and intentional EMI that I'll be talking about today, and cybersecurity are also there. And well, there are some AI and ML for EMC and SIPI problems. So if you're interested in participating in the symposium, these are the dates. Sorry for this. And I think, well, the hard deadline for the papers is usually early 2026. So you see there about January and February, depends on what you're looking into. So the traditional special session papers are usually in January, but there is also the workshop and tutorials for people who would like to do some demonstrations there. There is also some deadlines. And feel free to contact me if you have any further question on how to apply to this Congress or any other activity on the EMC area. So now I'm going to switch to my presentation. So today I'll be speaking about intentional electromagnetic interference. So just to let you know, oh, it's not working. Okay. I'm an assistant professor right now in the National University of Colombia. We call it in Spanish Universidad Nacional de Colombia. And this talk that I'll be giving today used to be my distinguished lecture when I was a distinguished lecturer for the EMC Society in the period of 2022-2023. So, I mean, it's a little bit out of date, but I believe that the things that I'm going to put today in front of you they're still to some extent valid, and the trends are usually not changing that much within the years. So the work that I'm going to show today is actually being put together after about 10 to 15 years of work in this domain. There are some institutions there that I'd like to acknowledge, because not all the material that I'm going to show today is mine. I'm also looking into the work of other colleagues. But basically, the big majority is coming from my work at EPFL in the Swiss Federal Institute of Technology. This is a picture of myself receiving my degree about 10 years ago. Back in the days, I didn't have this big size and I didn't have a beard. Oh, of course, you know Professor Rashidi. There is also some work that I'll be showing today that we did within a European project. So I'll be showing some results that we achieved together with the University of York, and my past position at Abu Dhabi in the Technology Innovation Institute and the Directed Energy Research Center. So I'd like to acknowledge all of them, because for several reasons, this is not only my work, but others' work. So when we talk about intentional electromagnetic interference, we're looking at electromagnetic interferences that are coming from a deliberate point of view. So there is a human being trying to create some very intense electromagnetic fields to disrupt systems. So IMI is usually associated to a defense problem. So we're looking at defense-like problems. And nowadays, I think with the unfortunate situation worldwide with the different conflicts that we have across the world, this is becoming much and much more important. So IMI is also associated to high-power electromagnetic sources. So we're looking at fields that are very high, so kilovolts per meter in amplitude, of magnetic fields in the range of 100 of amps per meter or so. And these are typically out of two origins. When we're looking at naturally made fields, we're looking at lightning, electrostatic discharge, geomagnetic storms. So this is like the old school EMC problems, and that are still, of course, under study. But when we looked into a defense-like problem, we're more looking at man-made fields. So here we're looking at nuclear origin EMP fields. So you have the high altitude EMP, which is when you detonate an atomic bomb several kilometers above the ground level. And the source region EMP, which is going within the region of influence of the atomic detonation. What I'm going to cover today is mostly transportable sources. So these are, depending on the classification that I'll be explaining afterward, they are hyperband, mesoband, or hypoband. And well, for the past, I would say 30 years, there's a lot of work being done in simulators. So these are fixed installations in which you will be simulating EMP or microwave testing. So this is more or less the domain, but as I mentioned before, I'll be mostly looking into the transportable sources today. Why is it so important to talk about the transportable systems? The most important one is that since they are transportable, you can operate them hidden in a truck or any aircraft or ship or vehicle. And this is a picture that dates from 2014 in IEEE magazine, when they were discussing the possibility of disrupting a data center with a very simple suitcase carrying an EMP generator. Well, back in the days, it was not anymore an idea. It was already feasible, and nowadays it's very common, especially in conflicts when you have unmanned aerial vehicles, like drones or any unmanned system is very susceptible to such type of fields. The big problem is that you can do this anonymously, so anybody could do it, and you are not aware of who is going to, who is behind all these attacks. Let's call it an attack. And as of today, I believe, you have range of influences in the range of a kilometer or even more, depending on the power that you are applying to your antennas. So today's talk is also dealing with antennas, but more on the high power side, and I'll be talking a lot about time domain antennas. These are examples of what you can find in the literature. These are systems that have been recently published by the United States. So this one is the Thor system. This is, I believe this was set up in Kirtland. This is Albuquerque in the south of the United States. It's a system that has been put together to do active denial of unmanned aerial vehicles. So this is to take down drones. There is also some competitors, Epirus. I think this is an array of antennas. And in principle, it's also able to take down non-cooperative targets. So this is a typical picture of what you can see in the internet. This is taken from a French company. The idea is that you have a swarm of drones that are approaching towards a facility or any restricted area. And for those that are non-cooperative, you should be able to take them down within distances of above a kilometer or so. So the HPM system, the high-power microwave system, is supposed to be able to have an area of influence of a given size, and depending on the field amplitudes, being able to take down the swarm of drones by acting on the electronics or in the guidance system or in the positioning system of such elements. And as I mentioned before, unfortunately, it has become very trendy due to the conflicts that we're experiencing in the north, the global north, and well, the recent attacks in Ukraine and Russia, etc. So this is what we call an IMI threat. It's intentional electromagnetic interference that is put together for damaging a system. And it could be not only a drone. I mean, for the European project that I'll be talking about today, we were looking more at a society problem because transportation, energy, security systems are all working together with computers. Our systems are also vulnerable to these types of threats. So we were looking at the susceptibility of an entire system, not only an equipment, but an entire system in the service provision. So just imagine the metro of Sao Paulo being, for some reason, attacked in its IT operation by such systems. So these are the kind of problems that the European Union was looking into 10 years ago. And that's most of the results that I'll be presenting today are coming from these lessons learned of these projects. But this is not new. I mean, it's probably new because of the small size of the sources, but it all started in 1945 with the first, nuclear detonations worldwide. It was observed that the nuclear detonations were able to produce very large fields coming from electromagnetic pulses. And since then, the electronics protection has become an issue. And for about, I would say, 40 to 50 years, there is a lot of work on the protection of critical infrastructure against nuclear EMP. So after 1990s, there was a commission in URSI that started looking into the high-power electromagnetic phenomena, but not against nuclear EMP, but the smaller things, because you were able to produce high-power microwaves in the laboratory, not anymore with a nuclear bomb, but with a microwave generator. So for the first 20 years after 1990, there were a lot of work on developing new sources and new methods to protect and to test the susceptibility of electronics against those fields. And nowadays, it has become, I would say, a more commercial issue because now you have drones and you have other types of non-cooperative targets that are susceptible to those fields. And I believe it's under the interest of any government to have tools to take care of that. So what we did basically in these projects is take all the work that was done in the previous years and just make an update because the frequencies, as I will be showing afterward, are higher than the usual ones that you deal with in nuclear EMP. So let's start with a very small introduction to nuclear EMP and especially the high altitude electromagnetic pulse. So this is the detonation of a nuclear bomb at least 40 to 100 kilometers above the surface of the Earth. And in principle, the idea here is that the detonation will be able to produce a very widespread pulse with the size of a country-sized pulse that should be able to take down particularly transmission lines. I mean, there is a lot of disturbances that will be induced in very long transmission lines and man-made electronic equipment. As a matter of fact, back in 2019, the first Trump administration issued an executive order on coordinating national resilience against nuclear EMP. So even though the Cold War was over, I would say the past 5 years, the US has been considering, again, the possibility of using high-altitude EMP against them. But as of today, there is no attack that has been reported. And all what we know is basically based on the work that was done during the Cold War. And I believe it's a very well-established science, and we know very well what to do against those. This is just a picture of the type of fields that you are experiencing when you are looking into high-altitude EMP. The IEEE 61-2-9 looks into the waveforms. So there are many phenomena involved there, including gamma ray acceleration with the magnetic field of the Earth. And, well, there are some other phenomena that will bring, put together, you can decompose them into 3 pulses after a nuclear detonation above the atmosphere. And the first is a very short pulse with a duration in the range of tenths of nanoseconds. So we're looking at a 20 to 30 nanosecond pulse with rise times that are in the range of nanoseconds. So they are responsible of generating many frequency content that could be used against electronics. The second pulse that we're looking into is in the range of microseconds, duration and rise times also in the range of a microsecond. And I would say we know very well how to take care of this because this falls within the spectra of lightning. So this is very common to have lightning protection. So the techniques that you will be used are the same. And the third pulse is a very is not very energetic, but is I mean the amplitudes are very, very small, but the durations are in the seconds range, and therefore there is a lot of low frequency content that is very dangerous to very long lines. Specifically, we're trying to protect transformers, basically transformers, against such a low frequency excitation. And this is falling within the same content of geomagnetic storms. So I would say that lightning and geomagnetic storms are taken care of very well. And therefore, if you want to protect against these pulses, you just need to look into that. But when it comes to the narrower one, then you need a little bit more of analysis, including high-frequency analysis with numerical electromagnetics or transmission line theory, as I'll be showing afterward. These are the usual rise times and durations of the three pulses. So as I mentioned before, nanosecond, microsecond, and second range. And these are the resonance sizes that you are expecting for such excitations. And therefore, the concerned systems are different in size. So as I mentioned already, for the fastest pulse, we're mostly looking at electronic components, whereas for the intermediate time and late time, you're looking at very long or distributed systems. When I'm talking about IMI, I'm looking into fields that are usually between 300 megahertz and some gigahertz. And this is a plot of the spectrum of a nuclear EMP that I was discussing before. This is the spectrum of lightning. When I talk about IMI, I'm looking at the blue curves that you have here. So you can already tell that we're working at the very high frequency compared to the previous works against EMP. What I'm trying to put here are the field amplitudes. I mean, this is power density, and these are frequencies that are usually coming from radar systems. There are some hypoband systems that fall within the same range of frequencies, and the mesoband systems are usually smaller because they are based on quarter wave oscillators that I'll be showing afterward. So these are the three types of systems that I'll be discussing today. If you want to compare to a known system, jammers are probably the closest ones, and jammers don't have as much energy as perhaps the sources that I'll be discussing today. And if you want to talk about the resonance sizes, they're all very small. So as you can see, the resonance sizes, depending on the type of waveform that we're trying to analyze, since they are within the picoseconds to nanosecond range, they are very small. So we're looking again to electronic components, cabling or antennas, or again, electronics. Basically, electronics are very susceptible to these types of fields. So what we try to do in the European project is to set up a risk assessment methodology to be able to predict the possibility of disrupting a complete system with such a tool. And the problem with risk analysis is that you never know what is really going to happen, of course. That's the idea. The most important thing is that the issues that you are able to produce with such a system is uncertain. And the mathematical modeling of such events are complicated because you're dealing with man-made things. You're dealing with deliberate use of of electronics, and it includes a lot of uncertainties that we were not able to tell, but at least from a technical point of view, we were able to at least dimension the risk by considering some of the facts that I'll be showing afterward. So how did we work? As any risk analysis, we were looking at the consequences, the likelihood of such a threat, and the hardness of the system. The idea here is that the risk is proportional to the consequence. If you're looking or considering the loss of lives or any economical impact, any legal impact, well, there are several ways to dimension the consequence. But if you want to term it in terms of money or other types of ways of measuring a consequence, then you might already know what to take care of and what to neglect, right? And of course, the most important one here is life. I mean, you are concerned about the life of patients. So we were looking, for example, at hospitals. So hospitals were of major impact. Transportation systems didn't have the same impact as probably banks. For example, banks have more important consequences when you are doing the analysis. So it depends a lot on what infrastructure you're looking into. Then you need to consider the likelihood. How possible is that someone will approach your facility, will approach your institution to do such a harm? So there are some subjective considerations in terms of the type of institution you are. Of course, when we come to defense-like problems, there is a very high likelihood if you are in a war position, but if you are more a civilian infrastructure, the question is, how likely is that some civilian will come against your facility, and that has to be taken care of. There is also the possibility of deploying such weapons against your system, and there are some technicalities that need to be considered when you are calculating those likelihoods. And then it comes the EMC side, is how hard is your system against such a threat? How well protected you are? And therefore, there are some EMC methods that we were looking into to be able to tell whether a system was protected or not. So let's just start by looking into the likelihood. So how likely is that somebody will deploy an IMI source against your facility? And here there are three criteria that we were looking into. The first one is the transportability. So how easy is for someone to bring that tool against your asset? The availability in terms of how feasible is the weapon in terms of the technical expertise required to do that? Because this is not something that you can buy on the internet, although there are many people that say that there are many things in the internet that can be already used. I kind of tend to disagree with some of them because there are literally very, I would say, highly skilled people required to build such a tool. And the last one is the accessibility. This is more on the security side. How accessible are you? So if you're looking into a hospital, how possible is for someone to come inside a hospital with such a big tool and deploy it? Or if you're looking into a bank, or if you're considering, for example, we were looking at airports, which were very important back in the days, and still they are, is how feasible is that someone with a weapon will be able to be inside your airport, etc. And when it comes to the availability and the likelihood, there are some parameters that we need to consider in order to be able to understand how feasible a high-power electromagnetic source is. So I'm not going to spend much time here, but the idea is to characterize very well the type of sources that you're looking into. And here we work in time domain and in frequency domain to understand the most important parameters of the pulses that you are generating, the resonance frequencies and all those. And depending on the type of waveforms that you are able to produce, we fall down within a classification that is widely known nowadays, which is the band ratio of your source. The first question you need to understand is how narrow band or, let's say, hyperband is your source. So what I'm showing here is a spectrum of a given signal. And what we try to do is to look into the frequency content of such pulses and find what is the highest frequency possible and the lowest frequency possible, in which you are able to integrate 90% of the energy of your pulse. And depending on the ratio of these two frequencies, you can tell whether your system is a hyperband system, mesoband system, subhyperband, or hyperband system. So a hyperband system is a system in which the signal generated has more than a decade between the highest and the lowest frequency, and therefore you can say that there is a band ratio of more than 10. So you have spread all your energy, the 90% of your energy, within a decade or more. And as long as the pulse, let's say it's hyperband, then you are looking at several frequencies that are going to excite electronics, and therefore that is one of the reasons why I was asking before about the time domain parameters of antennas, because you need to understand how possible is to radiate such a pulse. And then you start to go to a narrower and narrower pulses. So subhyperband and mesoband sources are pulses with a ratio in the range of 10 to 1. So it's becoming smaller. And then you have the hypoband, which is a narrowband signal, because almost all the energy is contained in a single frequency. And that's the usual in radars or CW systems. And we know a little bit more about how to work with that. But understanding the physics and how to radiate and couple a widespread spectrum was a challenge back on those days. So this is a typical example of a radiating antenna that is able to radiate pulses of very short duration. We call it ultra-wideband antennas, or within the EMC people, we call it impulse radiating antenna, IRA. And I think Everett Farr is an expert in such systems, and that is why probably we were trying to address that problem. This one is what we call a half impulse radiating antenna, because we are cutting in two this antenna, and this works very much like any parabolic reflector. The main difference is that we have a transverse electromagnetic wave that is going to hit the mirror and is going to add in phase in bore side. And you can demonstrate that the bore side signal is proportional to the derivative of the exciting pulse. So in terms of the derivatives of voltage that you need to drive such an antenna, you are looking at pulsars as of today with 10 to the power of 15 volts per second to excite the main lobe. So we're looking at pulses of 100 picoseconds, 80 picoseconds of 30 to 50 kilovolts amplitude. And with this, you are able to produce fields in the range of 800 kilovolts per meter with an 80 picosecond rise time. So this is a huge derivative that is usually used to take down, this is what we call I forgot the name, the puncture effect in electronics, and you're able to break the transistors. And well, if you apply it correctly, what we have found is that you can switch down computers, you can probably damage, if the electronics are not very well harmed, they can be somehow damaged or at least latched up. That's what we call the latch up effect. This is another example. This is a mesoband source. This was developed by the French government. So this is the French-German government. It's the ISL Institute. This is a helical antenna, like the ones that you can see in communication systems, but the pulsar is usually working below 1 gigahertz. The usual frequencies are within 300 to 500 megahertz. So the size of the helical antenna becomes longer, and the loops become wider. In principle, the more turns you put into the helical, the more gain you get, but there is a saturation point in which you can put more turns, but you're not necessarily adding more gain to the antenna. This is an example of an antenna that was fed with a very fast pulse, and depending on the resonant frequency of the antenna, then you will filter out the DC components and be able to radiate a single, or not single frequency, but very mesoband signal. Typical examples are, to excite these antennas, it's 400 kilovolts pulsars, not very energetic, 19 joules, which is not much for a pulse. But you're able to produce fields in the range of 225 kilovolts per meter, for example, for systems from the company Diehl. This is a German provider. I believe that this one was able to produce fields in the range of 10 kilovolts per meter at 10 meters. I don't remember very well, but well, you can have all the references here. All this has been published in the literature. But the idea here is that you're able to produce a very tuned signal, but it's still with some bandwidth able to couple better with systems that are not exactly tuned at the same frequency. So this one, I think it was used to tune to the 400 megahertz pulse that was used to activate improvised explosive devices in Afghanistan. I mean, I'm not saying this was deployed in Afghanistan, but they were looking into the car problem. The door opener was working within those frequencies, and those were used back in the days to drive the improvised explosive devices in the Afghanistan war. And then you have the hypoband sources, which are low-power microwaves or high-power microwaves. And here you have all sorts of powers. They are very, very energetic because there is a lot of power that can be delivered with those systems. And here we're looking at solid-state devices with very low peak power, or if you want to have a lot of peak power, we're looking at HPM tubes, which are, of course, very heavy and very difficult to drive because you need to have a lot of backup power to feed this. And this is a personal opinion, it's a very untransportable source. Although many of the standards against this type of systems consider hyperband sources, I believe that that's a little bit too much because those systems are not necessarily transportable. But as a matter of fact, over the past 15 years, there is a lot of work in reducing the capacitor sizes. The main power has become much more transportable, and perhaps nowadays this is easier to do. If you want to look into the type of tubes that you want to use to do a hyperband source, so we usually say that the limit is within 5 to 10 gigawatts of peak power. Usually the pulse energy is within the kilojoule range. So remember that here we were looking at 19 joules, not very energetic, but very well coupled. Whereas here there is a lot of energy that is going to be delivered. And therefore, this is very useful for thermal breakdown. So here you're melting the electronics. So the usual candidates are traveling wave tubes, vercators. It's a very inefficient source, but very low cost source. You have magnetrons, like the ones that you have in your microwave oven, but let's say of higher power. And well, Milos, BWOs, and all that. So there is a very good book by Ben Ford and Shamiloglu in New Mexico, in which they are usually publishing every 5 years a new version on the recent advances on the production of high-power microwaves, which I'm putting here for those who are interested in such a field. So just to show you some real-life examples, this is probably the most famous one for those who are in our field. This is the JOLT. It was, again, Air Force Research Laboratory in New Mexico. I think this is sitting down in the University of New Mexico nowadays. What I have heard is that this was put together, again, for the war in Afghanistan back in the days. This system is able to produce I think this is responsible of the 800 kilovolts per meter with 80 picosecond rise time that I was discussing before. Then in 10 years later, this system, this is built by Diehl. Diehl is a German company, but the NATO has put it into a car, and it's called the car stopper. So there are some videos on YouTube where you can see this working. Basically, this is a very small Marx generator driving a loop antenna that is sending a pulse against someone behind you, and you are able to stop the car that is behind you. That is the idea. They have also shown how to work with this against non-cooperative boats. So there are some examples in the video of people with, well, these small vehicles in the sea, and they are able to stop them. This is also an example of a hyperband source. So, here I'm showing how difficult it could be to transportate this. This is a Vercator, and actually I think this picture I took it. This is in Switzerland. It was sitting down in Switzerland. It's a system probably this big. And well, in terms of the pulse power that you need to drive this, we're looking at pulses in the range of 300 kilovolts and probably a microsecond or less duration, 100 nanoseconds duration. So the pulse power to drive this is much more important. And so I don't believe it's a very transportable source. There are new things that I could find on the internet when I put this presentation together. This is from 2023, various research. They are also in the south of, I mean, this is New Mexico again. I'm not sure what type of system this is, but by looking at the antenna, this looks like a biconical antenna with some bands. I believe this is an ultra-wideband system, so I believe it's a hyperband system. The same company Deal, they are selling the Skywolf. This has been advertised against drone swarms. And this is basically a 400 megahertz horn, so something this big. That is being fed with the same system that you are using in this one. And it looks like, I mean, they are able to take down drone swarms. I haven't seen it operating, but I mean, this is more or less the promise that they used to have in the website. I'm not sure if it's still there. And this is a company in France, it's called IEEE. They are advertising what I believe is a hyperband system. I think what they have there is a klystron, so I think it's a 10 gigahertz tube driving a cylindrical horn antenna, and this is basically the antenna I was showing in the very first slide when we were looking at the drones. So those are the systems that we're looking into when we are trying to protect against IMI. The second part of this talk is dealing with what you need to do to understand from the EMC point of view how well protected you are. And here, what we try to do with all the systems that we're considering is to try to develop a topological diagram to understand the penetration of the field at all the levels of the propagation of the electromagnetic field from the outside to the inside. So here, this is a typical example of a barrier infrastructure. These are very common in Switzerland. So you have a field outside that is going to penetrate towards your electronic equipment, and depending on the layers, well, there will be some attenuation of the fields that you need to calculate. So here I'm just showing the transition between the outside into the soil, into the reinforced concrete enclosure, then into a shielded cabinet, and then coupling into the cables. And that is the idea in general, that how we try to work to understand the EMC hardening of infrastructures like hospitals or, for example, nuclear plants are very easy because they are very well built in terms of the topology. It's very easy to tell all the shielding layers. But if you look into a civilian infrastructure like a regular building where no EMC aspects are taken care of, then it becomes much more difficult to do such analysis. But that is more or less the idea. Well, from the numerical point of view, because of course this has to be done numerically. There are some analyses that can be done analytically, but we ended up working with numerical methods, and there are many very good methods out there, 3D codes, transmission line codes, etc., that you could use. But the main idea is that if you know the high-power electromagnetic environment, you will be able to calculate all the transfer functions that are responsible for the interaction within the apertures, non-adverted apertures, all the shielding mechanisms, finally coupling into the cables and transporting all that signal to the input of the circuits, and then be able to understand if the circuit is failing, what system function is going to fail. So this could be, for example, the computer that is working with the railways. This could be the communication systems between a cell phone and an emergency system, or the TETRA systems in defense or in emergency. So there are many things that could fall within this framework of analysis. And what we do is that if you know the HPM environment, you will be calculating transfer functions of the, for example, soil plus the rebar concrete and understand what is the field in the next level. Then if it's a shielded enclosure, what is the field in the next level, etc. To be able to tell what is the field out that is going to excite the electronics. Or if you look at in the cable coupling side, you do the same analysis to predict the voltage and current amplitudes and compare to susceptibility levels and see whether this is going to disrupt or not the electronic system. So these are typical examples of the buildings we were considering. Actually, it was me who drew this one. The whole project, we were working with this one. This is a civilian infrastructure, and we were considering the possibility of attacking from a window to the inside. So this was performed probably 10 years ago, or a little bit more. Back in the days, there were some drawbacks in terms of memory and CPU requirements to run such a calculation for a very high frequency field. So these were systems that could be 1 gigahertz frequency. We were mostly working with 400 megahertz because of the reason I was explaining before. And then the other problem is how able you are to model all the physical discontinuities that, the physical discontinuities that can be affecting the whole system. So if you look into EMC, we all know how to shield, we all know how to protect, but the usual problems in EMC are coming from errors during the installation phase of filters. So the question was, how perfect are these windows to avoid the penetration of fields, etc. So these are some examples of the simulation results. We were using numerical codes to predict the field inside the room by attacking from outside, and then we will use 3D codes to do that. So it's the diffusion along the walls for the penetration through apertures. Then with cable network codes, be able to calculate the field to cable coupling. So if we had a computer or if we have some desktop here, and the raceways, how able we are to induce fields there. And then with circuit codes, be able to understand what would be the possibility of installing surge protection devices at the small, for a small equipment and still be working, etc. But of course, as I mentioned before, the codes are not perfect, so we also had to do some experimental work. And this is more on the usual EMC measurements that we do to understand the shielding effectiveness. So, well, shielding effectiveness is a very easy one because you're basically trying to test how much penetration you can have within a window or any aperture. So here we had doors, and well, you're always trying to, calculate how many attenuation you can provide from one point to the other. So that's like a very classical one. But the most challenging ones were probably cable raceways because, these are industrial-like raceways, and there's a lot of metal there, and one could tell, well, probably this is very well protected, I shouldn't take care of, but we always had this question whether this was true or not. So we had to go into the laboratory and literally inject signals into different types of networks. So we were considering low-power cables, network cables. So there are different categories of cables, category 7, category 6, shielded, unshielded, telephone lines, and we had to build some, test fixtures to interface, communication with not communication, sorry, but radio frequency equipment with, the different types of standards. So this is telephone line, this is a network cable, these are low power cables. And at the same time, trying to reproduce these experiments with transmission line code. So here is the example of the same raceway, so this same raceway being put into a transmission line code in which we're trying to reproduce exactly what you have inside. So there is a challenge of trying to put all the cables inside, being very deterministic in creating those scenarios to be able to say, well, this is matching or not the simulation. These are some experiments we performed in Switzerland. So you can see here we were injecting into cable raceways. We had computers, literally computers, loading all these raceways, and with some vector network analysis, while trying to tell what is the transfer function between one point and the other, and being able to verify the tool to then extrapolate to a big building and be able to do all those calculations. So these are some of the results we were using. What you see in the dashed lines are experimental results, and what you see in the solid lines are the results with some codes. We were using commercial code, CST, and this is a tool from the French defense. It's called the crypto code. So we were trying to reproduce, experiments and simulations, and they work very well. I mean, there are some discontinuities like what you have in a typical raceway that we were able to reproduce very well in simulation. So we were very satisfied with the results, and practically one of the main conclusions is that with numerical methods is enough, at least up to some hundreds of megahertz, to predict the response of cable raceways. We also did some work in reverberation chambers, because for higher frequency fields, we didn't know what to use there. And the main drawback is that these cables that are not necessarily well adapted from a microwave point of view are not coupling very well into the cables. I mean, those fields, here we were working up to 6 gigahertz, are not necessarily coupling very well into the raceway, but we need to understand to which extent those levels are high or low enough such that high power electromagnetic excitation could still induce important currents. So what we did is that we put all those systems inside a reverberation chamber and tried to derive some transfer functions between the sockets. And this is more or less what you obtain. What happens is that we were measuring with all the cables. We removed, so we disconnected the measurement systems from the raceway just to understand what is the influence of the raceway. And then we removed all these patch cords to be able to understand what is the influence of these small patch cords. And what you see here in black is the measurement card alone. And when you start to connect the patch cords and when you start to connect all the raceways, you can see the increase on the receive level, which is no surprise, basically at low frequencies. But at high frequencies, there is basically very few differences between connecting or not connecting the raceway. So this is just to confirm that for higher frequency fields, there is less opportunity to couple, but still the transfer function could be important and be able to induce a lot of voltage and currents at the electronics component level. So this is the comparison of 3 types of cables. What you see here in AC, these are the low voltage power cables. T1 to T3 are telephone lines, and these are network cables. So as you can see, the most susceptible ones are the voltage cables, of course, because they are not shielded, followed by the telephone lines, and then the higher you have the category, well, the less shielding you expect. So you have here the maximum induced level, the mean level, and the minimum level in the reverberation chamber. So with this in mind, we were able to derive some design rules to avoid any interference from the IMI. Well, this is an example of an unshielded measurement card and a shielded measurement card. And here is where shielding plays a very important role. You can add up to 20 dBs of protection or 15 dBs by using well-rated, category 7 connectors and trying to respect all the measurement chain. So this is very useful from the communications point of view because the bit error rate is going to be very stable, but then when it comes to IMI protection, it's also very beneficial. Then, just to close my presentation, the question is, okay, you already know how much voltage and current you will be able to produce. Now, how susceptible is electronics against it? And here, I'm going to come back to the standards point of view, because standards, as Vince mentioned, is the only way where we can more or less tend to agree to the same way of testing and the same way of communicating hardness to customers. So here what we're trying to address in terms of the hardness is how easy is to induce a voltage or current disturbances at the equipment level, and from a system point of view, how redundant is your system in case that you lose one electronic system? Are there any redundancies that you could be using to support the operation of the entire transportation system or financial system? So how we operate this is very, if I want to make a parallel, is very similar to radiated immunity testing. You have a device under test, you're going to produce a very high field. We have a field sensor to monitor this amplitude, and then with a camera or whatsoever, you are going to understand what is the immunity. So this is a classical immunity test as you do in EMC, but the main difference is that instead of using radio frequency amplifiers and RF antennas, we're using impulse radiating antennas for the hyperband and mesoband systems. And for the hypoband systems, then we fall within the same logic. So there are several publications by SC77C. I had the pleasure to work with them for about 5 years. The SC77C are responsible for producing all the IEEE standards on high power transient phenomena. So here is a list of all of them. Back in the days, this is probably 2021, 2022, all the red ones were being recently published. No, sorry, 2013, 2015. The red ones were being published, but nowadays all of them are finished. So I'm going to talk about mostly this one, 61000-4-36, which is IMI immunity testing. So there is no surprise that the standard is also looking at hyperband systems, mesoband systems, hypoband systems. The hyperband systems are used to test, a hyperband phenomena with fields in the range of 30 kilovolts per meter and rise times between 100 to 500 picoseconds. And pulse repetition frequencies from 1 to 1,000 kilohertz. So this is really to drive electronics very, very fast. And those levels are based on actual practice. There is no, up to the best of my knowledge, a system able to produce faster pulses than this. Probably there might be some couple of kilohertz out there, but this is probably the highest you can drive with a commercial pulsar. And these are the fields that you are usually looking into. So this is the same antenna I was showing you before. This is the sensor that we use to measure such a transient, and we will be, illuminating the target with this antenna for an entire day and trying to understand what is the immunity. This is an example of another source. This is one we built in Abu Dhabi. I used to work for the Technology Innovation Institute in the United Arab Emirates, and these are the systems that we were able to produce there. So this one is a very transportable one. It's only 1.2 diameter antenna, and the weight is 60 kilograms. So see, this is something you can put into a car. The solid-state pulsar, we were using 12 kilovolts with 100 picoseconds, and we were able to produce fields in the range of, here they are, 40 kilovolts per meter. So this is a typical waveform you can get in your oscilloscopes. So it's a signal that once you reach bore site, you are calculating the derivative of the input. So these are the fields that we were able to measure. As you can see, it's a very, very small pulse with a picosecond duration, hundreds of picoseconds. And this is the spectrum. This is the Fourier transformation. You can see it's very derivative at the beginning. You have a flat up to about 700 megahertz. And then, up to 3.5 gigahertz, there is a lot of content. So there are many resonances that can be excited with such an antenna. If you look at the mesoband test levels, then you have, again, fields in the range of tens of kilovolts per meter. In this case, it's 60 kilovolts per meter. Frequencies ranging up to 500 megahertz. And again, the pulse repetition frequency no more than a kilohertz. So this is the same antenna I was showing you from the German defense, from the ISL, being put into a small trailer. And the fields that you can produce with this are within this range. This is another example of what we built in Abu Dhabi. This one is a very transportable one. It's a 14 kilogram system, 40 by 40 by 40 cubic centimeters. So it's something that you can literally put into a suitcase. I mean, myself, I could carry it. And what you have inside is a quarter wave oscillator of probably this size. We're fitting it with I think it was 10 to 20 kilovolts DC source. It is not very energetic. And you can drive repetition frequencies in the range of 100 hertz. So these are the usual waveforms that you can measure with it. This is 15 kilovolts per meter at that 1 meter distance. Well, we like to work with analytical models. So what you see in the dashed line is just an analytical model to see whether we are able to reproduce the same frequency and all. And here you have a picture of the spectrum. So as you can see, it's fairly tuned around 400 megahertz. And this is what we were trying to do from the design point of view. So we were very glad to get good results. Then on the hypoband test levels for IEC, you should be able to produce fields of this range, 225 kilovolts per meter. From my point of view, this is very complicated with a transportable system. What you see here is a German system this is the Department of Defense of Germany. This is a system in Münster, and it's a 400 megawatt system that is able to produce tuned frequencies between 700 megahertz up to 3 gigahertz. Well, this is an existing system, but the question is whether you can transport this close to an airport or to a hospital or whatsoever. I don't think so. But there are some smaller versions, like the ones that we built in Abu Dhabi when I was there. It's the REDAT one. This is it's also a tube. So we were driving. I think this is a magnetron. It required a source power in the range of 8 kilowatts, but we were able to produce 1 megawatt peak. It's a heavy system, 350 kilograms, but less heavy than this one. This can be put in a vehicle. What you see here is some sulfur hexafluoride to avoid high voltage inside the cabinet, because there is a high voltage phenomena going on there. And this is the type of field that we can produce. So this is 60 kilovolts per meter during a microsecond or more. So this is a very energetic system. And if you do the Fourier transformation, you can have it here in blue. This is tuned to 1.3 gigahertz. So this is a lot of power. It's a very dangerous tool. And you can do testing, according to the IEC levels. The pulse repetition frequency of this one, we don't achieve. I'm not sure whether we were able to put, no, I think that the pulse repetition is probably 10 pulses per second and no more than that. It's a very inefficient from this point of view. So if I put all of them together, this is the hyperband, this is the mesoband, and this is the hypoband, then you can have a good set of testing sources to be able to test all the susceptibility levels that you need to put together to understand the susceptibility of a facility. What to do next? Once you understand the susceptibility levels, then you need to increase the EMC measures that you have in your system. So it depends a lot on the mission that you are achieving with the equipment. This is more looking into the possibility of the outage. Like for instance, at the beginning of this workshop, we were able to stay outside the building because there was this shortage of electricity. During half an hour, we were able to talk and we were able to have some coffee. There's no problem. And this is the type of missions that we call level 1 missions, because you can allow an outage of a long period. But when the problem becomes more critical, then you are not allowed to have hours or minutes or seconds of outage of a given problem. And therefore, the required hardening starts to become more important. In general, those systems which don't allow more than seconds of outage, we're looking at inherent protection. So the system is already protected from factory. But otherwise, you could start doing some partial protection or integral protection, trying to put a whole system within a protection scheme. And what we used to say is that you don't need HPM testing for level 1 and level 2. It's only for level 3 and level 4, in which it depends a lot on the policy, but several governments are interested in testing level 3 and level 4 equipment, especially for defense-like purposes. So what do you do? Well, it depends on the money allowed. The cost will increase as you start to put more technology on it, but the most important one is providing some additional shielding to IT equipment. So this is not only just the cabinet, but probably putting the cabinet inside another shielded enclosure. We're looking at ensuring the secure distance so that if there is any possibility of attacking your facility, then it's done from a safe distance. So the fencing and adding some meters from the entrance is important. By the way, this is something you can find in IEEE magazine in this volume. There is a lot of, I think this Bill Radasky, it's Bill Radasky who wrote this one. There are many things that you could do there. Improving cable layouts and protecting the windows. So this is adding some grids to your windows to avoid the penetration of fields. And then the cost will start to increase when we start to do all optical communications. So back in the days, it was probably expensive. Nowadays, I believe 15 or 10 years later, optical communications have become cheaper. So probably it's easier to do that now. And the installation of proper filters and devices. So back in the days, we were working with source protection devices companies that were trying to develop new SPDs to protect against such threats. Well, I would like to finish by just mentioning that if you're interested in such topics, there are some books that are there that are probably covering the past decades of work. I'm leaving them there. This one is coming from the latest meeting we had in Abu Dhabi on high power electromagnetics. It's the the Global EM Conference. This one is from Dave Geary, Richard Holt from Kinetic. Dave Geary is a private consultant, and Frank Sabat from the German Defense. They are both covering all these topics with much more depth. So I hope you liked my talk, and I'm ready to take some questions. Thank you very much. Any questions?
Very good presentation. Congratulations. Very interesting topic. Just a curiosity, talk about testing. You show us some anechoic chambers to provide this kind of test. I suppose that some special recommendation or special configuration should be carried out to do this kind of testing using.
Well, it depends on the type of source that you're driving. Since they are not very energetic, a typical semi-anechoic chamber should work. Unless you're driving with hyperband test levels. Here, the field amplitudes could reach very high fields, and usually the absorbers are not rated. Oh, shall I talk to the microphone? Probably, yeah. So again, it depends on the field levels that you're going to excite. And I would say that for the mesoband and hyperband systems, there is no need to add any additional because, all the equipment is working very well. But in terms of the absorbers, probably hyperband test levels are important to take care of because usually those absorbers are rated up to a 3 kilovolts per meter value. So higher fields could induce some deterioration. And then one of the major problems that we have is that since the signals are very fast, you need very fast oscilloscopes. So we're looking at more than 20 gigasamples per second back in Abu Dhabi. 10 gigasamples per second, above that is the requirement. So you need to have a good oscilloscope to work in time domain. And that is why I was questioning before whether there is any frequency domain technique that we could use to this. But again, frequency domain devices are very susceptible to such field amplitudes. So you are not able to put them directly with a spectrum analyzer, for example, and the gating is very complicated as well. So yeah, that would be my recommendation.
In this case, open area is not recommended.
What we usually do is open area test site. That's what we're usually doing. But the problem there is that you need to have regulations because you're probably damaging.
Okay.
So what we did in Abu Dhabi, for example, is to work in the desert. Not many people there.
Okay.
So yeah, it's a complicated.
Even the equipment should be protected again.
And the equipment has to be EMC protected.
Yeah.
So there are many things that in the measurement chain that need to be considered. But I mean, companies in this domain have already very good solutions to that problem. For example, for the measurement of the transients, nowadays you can do up to 3 gigahertz. You can do time domain measurements with fiber optic links that are connecting the sensors to the oscilloscopes without having to shield all the cables. So those are good news.
Okay. Thank you.
Any other question? Yes?
You mentioned cable layouts to protect structures. I know about PCB layers layout and etc. But cable layouts, what can we do to improve the cable layout that?
Yeah, like usually what we found out is that there is not much to do but just adding additional shielding because the layout is probably driving very small dBs, in the total transfer function. But here you want to attenuate 40 to 60 dBs. There is no layout that could help on that. It's literally putting some additional, metal on top, or there are some companies selling some braided shields that you could use to put all the cable inside and do some proper termination of those braids, or just adding filtering, like additional filters. So what we found out is that the most susceptible system, for obvious reasons, is the communication systems, because the antennas are in-band, and therefore limiters are the only options that you could use there. And redundancy, because if you lose your communication system, then you need to find another way, in another frequency to be able to work. So we worked a lot with train networks, and GPRS, back in the days, was the important one. We found it's very susceptible. So we had to migrate to other redundancies. Yeah.
Just another curiosity, is there some electromagnetic protection system to be used, like in
Sorry,
this case?
any?
Electromagnetic protective system. Like you made a comparison to submarines, for instance. You have a magnetic protective system.
Yeah, so inherently protected nuclear plants.
Yeah.
Nuclear plants are very safe
Yeah.
because those systems are by fabrication very well protected. So those are systems that we're on the safe side. Or did I answer your question?
I'm not sure. In fact, I try to ask you if it's possible to design some system that intentionally you can face this problem. Like in the submarine, you have the first for low frequency. You have the magnetic protect system.
So that same question I was asked during my thesis dissertation, and my answer is a personal one, is no, because there is nothing you could do. I mean, if we create some protection measures, human mind is always trying to find the flaws, and you always have something against you, right? So I think it's a trade-off between having good systems, but also as a society having good behaviors and being able to live together, because this is mostly coming from human mind, right? Yeah, that was my main conclusion. And there is another side of it, is that it is very costly to look into all the problems that you might have within a system. And I believe only military can take care of that. I mean, a regular bank, well, it will be very costly to have every single office of a building protected against IMI. And I don't want to live in a society like that, that is always trying to protect from all the sides, you know, it's very uncomfortable, I guess.
Okay, check.
Any other question? You had one, Vince? Oh, no, okay.
A curiosity too. Which the distance for this type of the system is effective? Which common distance, because we have the loss propagation, the loss penetration. I'd like to know which the distance.
Yeah. So
will
it
be
depends
effective.
on what you have, but what we look into, at least for drone protection, is 1 kilometer. But for these facilities, our recommendation is less than 100 meters is unsecured, because it depends on what you have, but it could be feasible. 100 meters, and the worst scenario is 10 meters is very easy to do things.
Okay, thank you.
Okay. Well, I think then this is my last one. Thank you very much for your attention, and I think we're ready to have lunch outside. Yes. So just remember that we have lunch served outside. Okay, so we should be back by. So we should be back by 2 p.m. No, 2:50, 1:50. 1:45. Okay. Okay. Thank you. You liked it?
Yes, I like this.
Okay.
It's a very important topic. People that work with the nuclear energy.
Oh, there are people here with me.
Yeah. Submarine. Somebody working for Navy, Brazilian Navy.
Ah,
Yeah, it's a very interesting topic.
okay.
It's a very interesting topic for a PhD.
So, yeah, I'm not very sure how
Because I think was the Brazilian
Okay, now we're on. That's okay. The people online didn't know to know that because they're not here and they're not part of the contest. So this one, this is one of my distinguished lectures as part of AMTA Distinguished Lecturer, and is on selecting the best suited antenna range for measuring antenna radiated performance. And we'll basically go over what range to select. Yeah. The importance of the range, of course, how one size doesn't fit all, what range to select, and then more important, what are you interested in? That's something that I have seen year after year. People ask for, a bunch of things when requesting a system or a facility to measure antennas. And they sometimes ask for a lot of things that they are not needed for what they're trying to do. So hopefully at the end of these presentations, you realize to put there what exactly do you need, because that can save you a significant amount of money in selecting a range. And then we'll go through like a small example of uncertainty and understanding uncertainty. So the importance of ranges. Now you can have the most incredible range in the world, or not the range, but the most precise, repeatable receiver, the latest version from Keysight or from NSIMI or from whoever. You can have a really cut-edge algorithm to process your data. You can have a very precise positioning system with 0.05 degrees of accuracy in the positioning. And all these things will be useless if you are not in the right environment to do the measurement. So you have to have the right environment to do the measurement. And just an example, I'm going to show you some data. So what this person was doing was placing a dipole, and that dipole was being rotated, but it was rotated off-center. So there was 1.22 meters to the edge of the circle where the dipole was rotated in the azimuth. And they were testing at, 12 meters away, roughly. But of course, because they were rotating this thing, there was a slight change in distance. And with the slight change in distance, there is a slight change in path loss. And we should expect something like that. There may be a slight more, irregularity due to the presence of the support structure in there, but something like that is what we should expect. And the data that the customer show, which is that blue thing, that blue amoeba, because it looks like an amoeba to me, that's what they measure. And the reason is that they performed this experiment in an anechoic chamber that had been designed to operate at 4 gigahertz and above. And this antenna, this dipole, operated at 400 megahertz. So they were effectively in an attenuated reverberation chamber without the tuners. I guess rotating the dipole was kind of like affecting some of those modes. So that is why the range is extremely important. The other thing about the range is that you're not going to find one size that fits all. These are not baseball hats. You have to have something that fits you. Why? Because, and that was the reason that the standard was set as a recommended practice, antennas come in many different shapes and many different frequencies. You can have your fully open quadrich horn, your open quadrich horn, can be a pyramidal horn. You can go with LPDAs. You can have on-chip antennas now. that you have to feed with like, probes. You cannot feed it with a coaxial. You can have very large parabolic dishes. You can have active phase arrays. All of these are different. They require different ranges. They have different issues with them. They have different gains, different directivities, different frequency ranges. You may have the ability to steer the beam. They can be directive, omnidirectional, different polarizations. Depending on the antenna that you're measuring, the approach may be better or it may be worse. So you need to understand which range to select. So let's talk about antenna range selection. And here is decision tree. That's what they call them, because here is the roots and here are all the branches. And as I said, there is never a perfect solution for all needs. Keep that in mind. If you're a test lab that serves many different industries, or you're a manufacturer that has many different antennas that you're manufacturing, you need to consider that you're not going to find a single solution for everything. So let's look at different ranges and what we may have. So first we have an antenna to be measured. That's the first thing. The first question is shielding. And years ago, over 11 years ago, I would have told you need shielding. But back then I worked for a company that made shielded enclosures. And, I have to eat. And I have to, dress myself and buy things for the kids. So I would have told you, yeah, you need shielding. By all means, you need shielding. But I will tell you that now, in most cases, I would say about 75% to 80% of the cases, antenna ranges don't need to be shielded. I knew that back then, but I was not going to tell you. So, there may be a reason that you need shielded. If you need shielded, you go in this branch. If not, we go through this other branch. You may need shielding because, you have very high power and you need to limit the amount of that power going out. You may need shielded because you're doing secure things. You work for a defense company and, you want to keep all your modulations and things secret. You may need shielding because, you may be working with modulated signals and there are similar modulated signals out there. That will be the case for cell phones to a certain degree. But think about shielding. Most industrial common shielding will shield from down in the 1 kilohertz range to about 40 gigahertz range. You can definitely shield about 40 gigahertz, but you have to get creative. Getting creative means you have to pay more money. Because, for example, your air conditioning vents for any anechoic chamber, those shielded vents were typically up to 40 gigahertz. Beyond that, you are above the cutoff frequency for those waveguides, and basically you get signals going in and out. So you have to put a baffle outside, covered with absorber, and then a secondary vent, and so on, and it gets more expensive. Typical indoor, and I'm talking just indoor, antenna ranges, you can go as low as 70 megahertz, provided that you can live with the potential error from that measurement, up to easily 300 gigahertz or even higher. We have done systems to measure up at 500 gigahertz. So if you go with a shielded enclosure, again, industrial shielded enclosure, you're paying for this amount of shielding that you don't need, because this is the ranges of frequencies that you're going to be measuring. And up here, you're not going to be able to shield. So think about that. Do you really need shielding? Safety. Now, if you're doing EMC, for sure you need to shield because you don't know what you're measuring. Think about it. You have some electronic equipment, you're just looking for emissions over a certain range. You don't know which range it is, you don't know which frequency. But when you're doing an antenna measurement, you know two things. You know how much power you're putting into your antenna under test, and you know which frequency it is. So you can block all other spurious signals by reducing your IF bandwidth. And also, if needed, you can increase the power into your antenna so you are way above that noise. How about the safety of personnel outside? So let's assume that you have your regular standard absorber, the blue foam that everybody is familiar with. That absorber typically can handle about 1,000 watts per square meter. There are some companies there that say 775. They're very conservative. Their absorber can handle 1,000. Some of the polyethylene foams that some Japanese manufacturers made, they have a little less power that they can handle. Polystyrene absorbers, also they tend to have a slightly lower power density because they're very good heat insulators, so it's more difficult for the heat to leave the absorber and get out. Now, human exposure standards, both international standards, the IEEE standard, they tell you that, you're okay for this range from about 2 gigahertz up to like 100 gigahertz. You're okay with like 10 dB watts per meter square power density for up to like, I think it's like 30 minutes exposure or something like that. So assuming that I have my antenna transmitting the maximum power that the absorber can handle, 30 dB, that means that, with 20 dB, I can put myself at the, exposure level that the standards tell me. If I have just a little bit more, 30 dB of shielding, I can be 10 dB below that level. And by the way, those are occupational standards. That's what they say for people that are working in that area, what used to be non-restricted areas or restricted areas. Non-restricted areas, I think, is 5 dB lower than that. But 30 dB of shielding, definitely not 80 or 100, is sufficient. So here is 8-inch pyramidal absorber. That's about 20 centimeters pyramids. And I took the material properties from one of the manufacturers. I don't remember which one of them. And here in this plot, I have the arrows pointing up is the reflection of the signal hitting the pyramid. And the arrows pointing down is the signal that goes through. So there is no metal backing. I don't have any metal backing to this absorber. And notice that almost regardless of the angle of incidence, 0 degrees or 45 degrees, basically my red and my green lines, already at 1 gigahertz, that absorber is giving me better than 20. So just that absorber at 1 gigahertz with no backing of any kind is giving you enough attenuation to be safe outside of the range, even if you are transmitting at the maximum power that the absorber can handle. And indeed, as you go higher and higher in frequency, that absorber becomes electrically larger and larger, and the attenuation through that absorber gets even better. So in many cases, yes, an absorber line room with no shielding is sufficient to attenuate enough to be safe outside. So consider those things when you're thinking, do I need a shielded range? Because shielded ranges, immediately your cost is going up because you have a shielded door. A shielded door is a complex design, especially if it has to be large. If you're bringing large antennas inside, it's very costly. Then you have to have vents for your air conditioning. Those are added costs. Then you have your filters to filter the signals going in and out, added cost. Everything that you mentioned shielding is adding cost. And let's assume that you are moving large antennas into that chamber. So you need to bring them in. And if you have a shielded door, those shielded doors typically have a threshold so that you shield against it. Or they're very, very complex doors like the ones that they have at INPE, that, you know, a platform goes down, the door comes out, goes to the side, the platform comes up so you can roll in. And those are extremely expensive. So going immediately for like, oh yes, I need shielding, that is a lot of cost to the project that you may not need. So, I don't need shielding. Then the next question is indoor or outdoor? And you know, the main question there, of course, everybody likes to go indoor. Everybody likes to be in the air conditioning. They don't like to go outdoor where it's raining, in places maybe it's snowing, it may be really hot. I have done plenty of measurements outdoors in hot weather in Texas, because the technicians will use the range in the morning when it was cooler, and they will let me use the range at 3 o'clock in the afternoon when that metal, you know, reflective ground was, you know, a good 100 and 110 degrees Celsius. So everybody likes to be indoor, but you're going to be limited by the absorber technology. So absorber technology, current absorber technology, you have ferrite tiles, you know, those, you know, have between like, you know, -6 to -20 dBs of reflectivity at the very low end. But once you go to higher frequencies, ferrite tile by itself is not going to do anything for you. It's as reflective as metal. You can have hybrid absorbers. Typically, most of them are polystyrene, expanded polystyrene foam. There used to be still some that were polyurethane. Some companies still make them. But, you know, that is still is going to limit at the upper ends, because typically these materials, they have to have a much lower amount of losses on them. Otherwise, they won't match well with that ferrite, and you won't get the benefits of the ferrite out of them. And then there's some tricks, like Chevy Chef arrangements that you can do at low frequencies to improve a little bit the standard absorber. There is also curvilinear absorber. The chamber at INPE has curvilinear absorber on the critical areas that apparently, I remember I designed it. At the time I was young and stupid. Now I'm old and stupid. And it was too thin, so it actually started drooping because of like the humidity and the way that it got. So it was looking terrible. We fixed that, but it was a pain. Then for like the, you know, 100 megahertz to about 40 gigahertz, you have your typical absorber. Foam absorber, the foam can be polyurethane, it's the most common one. You have polystyrene now that has improved quite a bit. It used to be mainly for EMC applications, for hybrid absorbers. They are controlling better how they pre-expand the little pellets, the little balls of polystyrene before they fuse it. So they can do materials that have very good losses up to high frequencies. They have actually tested them. A company out of the Netherlands, I was visiting them maybe a couple of years ago. They show me data up to like 75 gigahertz. And then once you go past 40 gigahertz and you get, especially in the 70 gigahertz and so on, then the paint it starts to be visible to the reflectivity, and that's when you want to go with unpainted absorber if it's painted. So that's the absorber technology, and that's what kind of like caps, for good antenna measurements, typically caps it around minus 100 megahertz. You can go with like some Chevy Chefs and push it down to like 70 megahertz. But as I said, typically 100 megahertz is the lowest frequency that I will recommend for indoor measurements. So let's assume that, you know, either you not the shielding or shielding, but the absorber can do the work for you indoors. Then next question is the far field feasible? Can you measure in the far field? Yes. Okay. What does that mean? What is the far field? Immediately everybody comes to like the R equal 2D squared over lambda, the Rayleigh condition. That's the lower boundary for the far field. So in 149, in IEEE standard 149, we decided to look, okay, what is the far field for different size antennas? We have different size antennas, electrical size, and there are different conditions. There is the electrical condition where the distance to be in the far field of that antenna is 5 lambda over pi. And then there is the geometrical condition. The geometrical condition is just you have to be far, far away. Well, what is far away? So again, in the committee we got together and there were some people that say, well, you know, 5 lambda. And some other people said like, no, 10 lambda. And we argued on that, we look at pros and cons, and we decided 10 times the size. So 10 times the size of the antenna is the far field. And then once we go to larger antennas, we go to the Rayleigh condition. So the far field is anything over this black line, this red line, and that blue line. And here they're in logarithmic scale, so that it's easier to read. But notice that electrically small antennas, you shouldn't use the Rayleigh condition. You know? So let's assume I have an antenna operating at 100 megahertz. My wavelength is 3 meters. So, you know, if the antenna size is 2 lambda, that means that my far field is at 60 meters. That's extremely, extremely large anechoic chamber. And it's a lot of expense. So I personally wouldn't do it, you know. You can do a tapered chamber, and that will be a little lower cost, but still, it's a significant amount of cost. And the same comes for like, you know, 100 megahertz. If it's a 3 lambda, now you're looking almost to 100 meters for test distance. Now, when we go higher in frequency, it gets a little better. 13.33 meters, that's doable. That's, you know, the IMPE chamber can do that. We can set up a range that size there. 45 meters, that's again, a very large chamber. A tapered chamber that size is easy. I have designed some like that. And definitely 30 meters as well. But notice that there is a limit, depending on the frequency and depending on the electrical size of the antenna, of what is doable indoors and outdoors. So keep that in mind. Now, if you can do the measurement indoors, then the other question is at which frequency you are looking at. Because typically, RF absorber is designed to operate better at normal incidence. That's the reason it's pyramidal in shape. And here we have, on the x-axis, we have the angle of incidence going from 0 degrees, that's normal incidence, to almost 85 degrees, that's almost perfectly oblique incidence. And, you know, I have different electrical sizes for the absorber. So we did a lot of numerical simulations for different size absorbers, different loadings from different manufacturers, and we tabulated all that data, and for a similar electrical size, we found what the biostatic reflectivity was for different angles of incidence. We came out with this plot. From that plot, we generated a series of polynomials, and those are the Rodriguez polynomials that give you an idea of the biostatic reflectivity. So if I have, you know, if I have to measure minus 20 dB side lobes, you know, and I have minus 25 dB of reflectivity, that's only 5 dB difference between reflected signal and direct for that side lobe. I could have a potential error of plus minus 7 dB. And that is with absorber at a low frequency, absorber that is, you know, 2.5 lambda, which is a significantly sized absorber. At 500 megahertz, that side wall absorber is probably like looking at 1.5 meters. So maybe you should look at a slightly higher frequency here for the 500 megahertz, than 500 megahertz. Taper chambers, they're a different animal in which you're not trying to attenuate the reflectivity from the sidewalls. What you're doing, you're trying basically to use it as part of your illumination, or you're trying for that to come with an angle that is very small, so your interference ripple is very long. And then basically your main absorber that you're concerned is the one on the end wall. So now you're looking just at normal incidence. So now it's easy to get a much better reflectivity on taper chambers. Now, there are other issues with taper chambers, and actually when we look at uncertainty, we look at some of the issues there. One of them is that they're not, oops, what are they doing to me? One of them is that they're not really good for you know, frequencies above 3 gigahertz. They become very frequency dependent, so you may have to tune the location of your feed, et cetera, et cetera. And, you know, you cannot do sweep frequency because of that, and no free antenna methods for like measuring gain. They're not a purely free space setup. They're a quasi-free space setup. The freeze transmission equation do not apply on them. And that's mainly what I said there. So, what do we do if, you know, to measure an antenna, the room has to be too large because the far field is too far away? Well, this was a known problem many years, and that's the reason that people develop near field and compact ranges. So we have, for electrically large antennas, and in general I say they are 5 wavelengths, but they can be larger than that. You know, these are not set in stone boundaries. You can go with a spherical or a planar or a cylindrical near field. There is a horn antenna. That little pink thing over there, that's a person, so it gives you an idea of the size of this. That's a very large near field system for like very low frequencies. Or you can go with compact ranges. This one, particular one, is to set to like go down to 700 megahertz. You can tell by the very long edge serrations over there. This is the feed section over here, and this is the positioner. So compact range reflectors, they have to be electrically large to operate. So in general, they're limited down to like 1 gigahertz, you know. 2 gigahertz is the normal standard products that are offered. But we have definitely done some operating down to 500 megahertz. I'm aware of 2 of them recently. It's the same as a far field. The same way that, you know, I have to wear glasses to be able to like see at a distance. I'm using basically a lens, in this case a mirror, to be able to like see the far field closer. And that's what we're doing. So it's a far field method. You can easily measure any type of antenna that fits in the area of like, you know, nice plane wave that it generates, the quiet zone. Near field systems, the simplest one is the planar near field system, but the planar near field system assumes that most of our power is going through that front of the antenna. So this is for directive antennas. I put there 15 dBi because typically you have to use a reference horn sometimes to do a gain measurement. So 15 is typically the gain of like some standard gain horns. But typically it's like higher gain antennas where you're only interested maybe a few degrees from the main beam. Because if you're interested more and more outside of the main beam, then you need to have a larger plane. And it becomes then larger and larger. In those cases, you may need to go to like a cylindrical near field system, and those operate well for like antennas that they have a narrow beam on elevation, but they're omnidirectional, or that you are interested in measuring the backload. For example, I know that was one of the requirements in the Anatel standard, that you needed to like measure the front to back ratio, which is an issue depending on how you mount the antenna. And I don't know why, because eventually you're going to mount these antennas to something. So whatever measurement of the front to back ratio you did goes out the window the moment you mount them. So, but hey, I don't work for Anatel. Hopefully nobody here does. I'm going to get in trouble with them. And then you have spherical. Sphericals are the most complicated, mathematically, and also with alignment and things like that. But any kind of antenna can be tested. And issues that you may have with this is, as you go to lower and lower frequencies, the type of probe, the type of antenna that you need to use to measure it becomes more complicated. Typically at high frequencies, we use open-ended waveguides. So it's just, imagine a waveguide, they chop the end of it, they sharpen a little bit the edge, and that's what we use. And for a spherical near field, especially the probe has to have certain requirements about the shape of its pattern. And it has to do with how many spherical wave modes do you need to represent that pattern. And typically you want just the first order pattern. And that's difficult as you go to lower frequencies and you have to use things like log periodics and things like that. We did some work years ago on optical probes, and these are lithium niobate crystals that basically, if you have a laser going through those crystals, it will modulate the laser depending on the electric field. So you can actually then demodulate the laser signal and get amplitude and phase. But they're only receive only, so they cannot transmit. But there have been some systems where they have pushed near fields down to like 100 megahertz, but typically there's some error there that you have to be aware because of the probe mainly, and the proximity of the probe to the device under test. Okay. So what do you do if you need to like do many different type of antennas indoors? So one thing is combination indoor ranges. So this one is at the National University of Singapore, their Temasek lab, and this one has a taper section This L shape is the actual outer shield. There is a shielded door there to access the feed section. There is a double door here to come in and mount antennas into the positioner. It has a roll over azimuth positioner, and that is used with the taper range that operates very well from 200 megahertz up to 2 gigahertz. Some of my friends over there at Temasek Lab eventually put a lens, a large dielectric lens at this location to increase the size of the quiet zone. Because you have a fixed distance, so your R is fixed. As your wavelength gets smaller, lambda gets smaller, your 2D squared over lambda means that you're like, something has to get, the R is fixed, lambda gets smaller, so your delta, your size, D, has to get smaller as well. So your quiet zone in a far field range will get smaller as you go higher in frequency. So here, in this location, they have a mount for a probe to do a spherical near field, and then for very high frequencies, millimeter waves, they have a planar near field scanner over there. So it's 3 different approaches in one single range. This other one, as you see, there is a compact range reflector there. Here is the feed, here is the positioner. And if I turn to the other side, there is an antenna that can be lower, so it's out of the way when not in use. And that can do far field range from 400 megahertz to 2 gigahertz. So then once you get to 2 gigahertz, you go to the compact range and go frequencies up. So this is another combo indoor far field range. We have done them also, so you have a far field range and a planar range at the end. So combo ranges are common because they give you the flexibility of having 2 different methods of measuring an antenna. An outdoor, do not underestimate outdoor ranges. They are inexpensive. There is lots of guidance on IEEE standard on how to implement them. And yes, people don't like to work outdoors, but sometimes maybe the cheapest approach. You can do compact ranges outdoors. This is in Arizona. This was designed by Georgia Tech, and it's a large reflector. They use it for both RCS. They're doing the RCS of a armored vehicle there, and also they can do antenna measurements on it. They're not common. This is the only one I'm aware of. And there were a lot of papers on what to do about the gaps between the panels that you get as the temperature changes. Here is an outdoor near field range. That's John McKenna over there. And this is at Oakland University in Michigan. And there is a feed antenna. This one was being used both as a quasi-far field, so they will do direct measurements at some frequencies, but also can do a spherical to far field transformation. Of course, you are measuring only half of the sphere. And here is a fairly recent implemented outdoor ranges. So people are still doing outdoor ranges. And here you see this is in the antenna under test tower. There is a slight elevation or azimuth over elevation positioner to set up the antenna. There in the distance, that orange arrow is pointing to this tower. That's the range tower. And in the range tower, you have a parabolic antenna as your range antenna. And here, you see another parabolic antenna. That is the phase reference link. Because while the antenna under test is rotating, this one is fixed. So you use that to get your phase reference and your phase lock. It's better than running what is, I think, close to 10-kilometer cable, which, will attenuate to nothing. So, any question on selecting the range so far? We're okay? Did I keep you awake after lunch? Go ahead.
Well, okay, I'm curious to know, I mean, how many orders of magnitude would it change if I go for an open area test site compared to a compact test range indoors?
So, it's going to depend on the frequency. But let's say that you, you know, an indoor compact range that operates down at 500 megahertz, I think will be probably in the 4 or 5 million, maybe more. Definitely over 5 million once you start adding the other things, the building, you know, all the extra things that. An outdoor range is definitely going to be much lower. You know, it's probably going to be 5 orders of magnitude lower or even more. The biggest cost is going to be the land. And of course, then if you go to Montana and set it up there, it's going to be very cheap. If you wanted to like set it up in Manhattan, then, you know, set up a compact range. I will say that here, you know, if you want a cheap outdoor range, go to Mato Grosso do Sul, and if you want to set up an outdoor range in Sao Paulo, don't do it. And, you know, I don't think anybody has that much money. So it's going to depend. And there is other factors that you have to think, you know, because you think on that, oh, my God, it's going to be 5 times cheaper. But again, what are you doing? What are you looking for? If you're in a production setup, that means that you have to ship your antennas to that place and potentially send an engineer over there if there is issues. And that's time. And if it's raining or it's too hot to test, you know. So those things you have to like keep in mind. And you have to keep, and as engineers, sometimes we don't think of those things. But those are the things that you can convince accountants about. Because you're going to tell them, hey, we're going to be wasting 3 days just to ship the antennas. We have the shipment costs. Then we have to have somebody living there. Or we have to send engineers there to do the tests. So in 3-4 years, you may recover that extra cost of the compact range. So, what are you looking for? Why are you measuring the antenna? I mean, if you're like some people I know, you do it because you are bored or you like it or, you know, and I have known those people. But why are you measuring? Think about that. Is it a production testing? Is it prototyping? What is the parameter of importance? Is it just gain? Or are you interested in silos? Are you selling that antenna to somebody that's going to deploy it as a communications antenna here in Brazil? And then you have to worry about the front-to-back ratio. So keep those things in mind. Those are important when you're trying to decide which range. Not only to build your own range, but where to send your antenna to be tested. What error or uncertainty can you live with? There is always going to be error and uncertainty. You know? And if the lab that you're taking your antenna doesn't give you that information, don't send your antenna there. Because chances are that they don't know what they're doing. What you're trying to to do, that will determine, what range you need. Is reflectivity an important parameter? And how much reflectivity? How about the gain uncertainty? I mean, do you want really accurate? Are you a national lab that you have to calibrate standard gains? How important it is. And convenience. Convenience. An outdoor range, again, may give you the best results, but it may be far away from production and subject to weather. So you have other costs. This is my slide that I put there so that I can drink water. while my antenna is being rotated. So, okay, my antenna rotate. There is your typical setup for a measurement. You have a positioner, you have a probe or range antenna, you have a position controller, you have a receiver, you have a source, and then you have to sample your phase by taking a reference from the transmit. But anyway, let's look at a problem. I have an antenna that operates at 18 gigahertz, and it's 12 lambda by 12 lambda. That's 20 centimeters by 20 centimeters, not extremely large antenna. And the diagonal is 17 lambda, 28 centimeters. So if I go to the standard, so, 17 lambda, some way here, go up here. I'm in the 575 lambda for my test distance. That's 9.62 meters. It's doable. I mean, I can get mixers there, multipliers, so that I'm using, I'm using IF for most of my cables, and I'm not having a lot of cable losses. So it's doable. Do we test at that distance, or we test further? What do you think? I mean, technically, I'm in the far field. I'm just in the lower boundary of the far field. So, although I have made an entire career in the measurement industry, I'm a computational electromagnetics person. Indeed, I'm also a fellow of the Applied Computational Electromagnetic Society. So I like to do simulations to improve measurements. So here I did a simulation where I have a probe, and I move it, from certain distance far away. I start moving it close, and then I rotate that horn on the E-plane, because I want to look at the side lobes. And I did two different horns. I did a 14 dBi standard grain horn, and I did an 18 dBi standard grain horn. I'm one wavelength away. And by the way, these ones I think were X-band horns, so I think I'm at 12 gigahertz. But, at a lambda, I don't even see a main beam. This is way in the near field. For the slightly smaller horn, I still seeing that there is a beam forming. My 3 dB beam width is terrible, doesn't match. But then I go to like d squared over lambda. And, yes, that's definitely not the far field. Incidentally, the original version of the standard to measure weather radar antennas for aircraft said that you could test at that distance. The new version does not. The new version tells you have to be at least 2d squared over lambda away, or use a near to far field transformation or a plane wave generator, be it a compact range or an array or something like that. Why? Because side lobes have become more important. And as you see there, between infinite, which is a true far field, and being closer to the antenna, there is definitely an error on that first side lobe and that second for this one that is showing two side lobes, and then here as well. And then my first null is not clear over there. Now, if I go to 2d squared over lambda, then I still have an error there for my null and for my first side lobe, and still I see I have a slight error there as well. Only when I get, to 4d squared over lambda, that gets a little better on the side lobe, and it is. So the answer to the previous question is, again, what are you interested in? If you're interested in the 3 dB beam width, you can be slightly closer than the far field. That's the reason that, my friend Benoit Derat, that used to be with Rodion Swords, now has moved to another company, show for one of the standards for like wireless devices that you could test closer than the far field, because it depends on what are you looking for. If you're interested in these side lobes, you need to test further away. So, the standard shows you that. This is a very old plot that goes back to like the 1960s when it was generated originally. But, we may have to be testing at 19 meters. That's a significant distance, both in losses and cost of the facility. That's where you're better off served with a compact range in that case. Or if you can get a phase reference, and that's becoming a little more difficult with some antennas, but if you can get a phase reference and measure phase as well, then you can go with a near field system, and it's going to be a better approach. What about reflectivity of the chamber? Immediately, every time I see a request for an anechoic chamber, immediately there is the minus 50 dB reflectivity. You can bet money on it that it will be there. Why? Part of it is that people go to like absorber manufacturers and see that the guarantee normal incidence reflectivity for the absorber is minus 50. Why is that? It's because it's difficult to measure less than minus 50. It's extremely difficult. You have to reduce your IF bandwidth significantly. That means that your test takes longer time because you're typically testing broadband. And time is money. And you're in a production setup. So you cap it at minus 50. Years ago they did it. But I have measured absorber where I had time because I was not in a production setting. I was in prototyping. And most of the absorber that you see out there, when you measure it at some frequencies where the guarantee level is minus 50, the absorber actually can give you minus 60, minus 62. Beyond that, you cannot measure because you're reaching the noise floor of the equipment. But you have typically a VNA that goes to one antenna that transmits your wave towards the absorber, and then you have another antenna that receives, and then you have a little absorber wedge between them to cut the crosstalk, and then you time gate, but then you have whatever cables go from that PNA to the antennas, so you have some losses there. Then you have the path loss down to the sample. Then you have a sample that is going to absorb, so you're going to end up with a signal coming back to the other antenna that is very close to the noise floor, unless if you reduce your IF bandwidth to like try to give you more noise to signal ratio in the device. And that's the reason that it's minus 50 there. But just because it's there, you may not need it. Let's assume that I have a chamber that has minus 40 dB of reflectivity. And I want to measure minus 15 dB side lobe level. A side lobe or some feature in the pattern that is at minus 15 dB. So the worst thing that can happen is that as I'm rotating my pattern to like point to that side lobe level that I'm trying to measure, the worst thing can happen is that it just happens to be that that main beam is pointing in the specular region of the chamber. and is basically being reflected, some of it is absorbed, some of it is reflected back to my source antenna. And for this argument, I'm gonna assume that my antenna has a very, very broad pattern, my range antenna. So the difference, the potential difference that I will have between my reflected signal and the minus 15 silo level that I'm trying to do is minus 25 dB. So there is this plot in 149. Actually, I think this one comes, the one on 149 I think is flipped. I think this one comes from my book. But if I'm looking at, minus 25 dB difference between reflected and direct, I'm right there. So whether that reflection is in phase or out of phase with the direct, I'm looking at a potential error of 0.5 dB. Half a dB. Half a dB on a minus 15 dB error. When you have time, go home, change that to linear units. Change that to linear units. We like to talk about dB, but sometimes we forget about linear units. And 0.5 dB difference at minus 25 dB level is nothing. Is, as they will say where I live, chicken shit. And you can get to those very small error levels just with minus 40. And the difference between minus 40 and minus 50 in error is going to be very small. But the difference in cost between being able to achieve minus 50 dB and minus 40 dB, that can be easily $100,000 or more. Now I'm trying to measure minus 25 dB silo level, and it happens to be, again, the planets align, and my silo happens to be at such a location that my main beam is pointing in that direction. Now, I know the chances of that happening are very small, but it can happen. This is basically potential uncertainty because you don't know for sure. So more than error, it is error, but this will be uncertainty. So now I'm looking at, I'm looking at plus minus 1.5 dB at minus point. And I said 1.5 dB, that's close to like 3 dB, that's half power. Again, change all these to linear units. Look at the difference between minus 25 and minus 26.5. You're at 0.000 something. Very small error. How about gain? Measuring gain. What if gain is the most important thing? So we can measure gain using the 3 antenna method. You get 3 antennas and you put them through a rotation. And then you have 3 unknowns, 3 equations. You solve for the gain of each of the antennas. That's an absolute method. But there are some cases where you cannot use this approach. This approach is derived from the free space equation. And you cannot use it on the taper chamber because, as I mentioned, the taper chamber, the transmission doesn't follow the free space equation. In a compact range, it does, but your feed antenna has to be a special type of antenna. And because of that, doing a rotation in here is not possible. But potentially you could, even that you're folding the optics of it. So in those 2 cases, and for those that want to know, here you have the free space transmission there. And here you have free space at a different frequency. Yeah, these two are free space, different frequencies. Here is the transmission inside the taper chamber. And this is what happens if you try to do a two antenna method, and this is numerically, in one case using CST, and on the other case computed the two antenna method inside a taper model. And you get a big error on your gain there. So for compact ranges, near field systems, taper chambers, for a lot of applications, what you do, you use a reference antenna. Use a known gain antenna, typically standard gain horns or dipoles, something that is calculable or that has been very accurate calibrated. And in that case, basically what you do, you measure your power, received by the antenna under test. You do the same measurement, but you put your reference antenna, and basically that ratio, together with the known gain of the reference antenna, will give you what the gain of the antenna under test is. Now, before I go into this method, or let's go here to the three antenna method. The three antenna method, what are the sources of uncertainty or error there? One you have is the alignment. You can try to correct for it as much as you can, and national labs, they spend lots of time trying to make sure that they align those antennas correctly. You have mismatch errors because the input impedance of some antennas is different from others, and those you can also minimize by putting 3 dB pads or 6 dB pads on the inputs. That's recommended for all kinds of measurements. And then you have mounting and dismounting the antenna, connecting and disconnecting. You can minimize those again by using torque wrenches. This is not a torque wrench. You don't know exactly how much you're tightening that. So use a torque wrench so you make sure that you are fastening that connector correctly. And there's other sources of uncertainty. Some national labs, they can do calibrations with uncertainties down in the 0.2 dB, even some claim 0.1 dB, but those take a lot of time, Most EMC labs, they promise about plus minus 1 dB, especially at lower frequencies. But that, if you're using a calibrated standard for your gain measurements, when you do this type of measurement, that uncertainty that the lab is telling you for that range is probably the biggest contributor to your uncertainty. But you have to keep that in mind. So sometimes we want to save money on those references. So, we want to send them to a lab that is cheaper. If you're going to take care of your standard, send it to a lab that has a better uncertainty, even if it's more expensive. Standard gain horns, do you need to calibrate them? Without calibration, a standard gain horn can be 0.3 dB, plus minus 0.3 dB of uncertainty, and that's basically because the typical curve that you use that comes out of the NRL lab report, that curve doesn't take into account some of the issues that you have or phenomena that occur in the horn, like edge diffraction, some of the internal diffractions from the changes in the horn, and there is a ripple on the gain that the curve does not show. But that ripple is about that, 0.3 dB, 0.25 dB, depending on the frequency. So if you're using a standard gain horn without calibrating it, just always assume plus minus 0.3 as your uncertainty from that standard. So understanding uncertainty. And I'm going to put there the most important statements about uncertainty that you'll ever see or hear. Both of them are from Mike Francis, that work in the electromagnetics field group at NIST. And he's now retired, but he's still active in AMTA. And the first one is that a measurement without an uncertainty stateless is useless. And it's useless because you don't know how accurate it is. I can measure the gain of an antenna within probably plus minus 1 dB uncertainty. And I can measure that with a ruler. I can go with a ruler, measure the aperture, go to an equation in Statsman or Balanis's book and tell you the gain of this antenna is about this much. And I bet I'm going to be within 1 dB, plus minus 1.5 dB the most. But at least I have to state that. So if a lab tells you, oh, the gain is this, without telling you an uncertainty, don't trust them. So you need to have an uncertainty. And then this is another important one that Mike Francis said. A rigorous uncertainty analysis is an oxymoron. Because if you can make a very accurate analysis of uncertainty, then it's called error, and you can correct for it. Uncertainty, by definition, is something that you don't know. You cannot know. So what I want you to get out of that is that you don't have to overcomplicate your uncertainty analysis. I was telling you earlier about Doran Hess, good old Doran Hess, with his 50-term error and uncertainty analysis assessment. That, NIST, the national lab, came only with 18 terms. And it's sufficient. 18 terms is sufficient. So there is no need for going for like 50 terms or try to identify 200 terms, because the chances are that a lot of those terms, they're going to have a minimal effect on the uncertainty. So no rigorous uncertainty analysis. That's an oxymoron. So what we're trying to figure out is how good the measurement is. Now, there is two different types of evaluating it. Type B, uncertainty evaluation, that is typically based on scientific judgment. This can be simulations. I have found, as a computational guy, I have found that simulations are very good to assess uncertainty. Because in a simulation, you can ignore all other sources. You can just look, okay, if I have two standard gain horns and I'm doing an extrapolation range where you bring the horns together, then you slowly take them apart, and then you do a polynomial of the S21 between those two horns, and then that polynomial, you take the limit as you go to like infinity, and you actually get the gain. It's a very known method for measuring gain. I can go and take those two standard grain horns and slightly move them side to side and repeat my experiment. And I can see potentially how much error I could get from a slight misalignment. And if I know from my mechanical guys, hey, we can position these horns within 3 millimeters, I can check that out and say, okay, the potential uncertainty that we have is from this term is this much. So evaluation is a good approach. And then there is a statistical method. And that's doing a lot of measurements and go over the measurements and try to estimate things. That's good in, and I have done that when I was at ETS because I was in charge of the antenna line. So there, of course, we were manufacturing antennas and measuring the same type of antennas all the time. And measuring in winter, measuring in summer, different technicians. So a lot of the terms of uncertainty, the technician, the weather, things like that, they could be factored within those measurements. Now, the other thing is to identify the sources of uncertainty. So, for example, the range antenna and the reference antenna properties. How directive are they? How, you know, if they're very directive, both of them, then alignment is critical. If both are very, you know, broad beam, then alignment is not that critical. Alignment positioning, which is related to that as well. Receiver system nonlinearity, you can get those from whatever equipment you're using. Noise, how noisy your background is. Drift, I think most receivers nowadays, they're fairly accurate that they don't drift that much. Impedance mismatch, you can reduce that by using pads. That's the importance of those 3 dB pads that you put at the input. You can reduce the effect of that. Leakage and crosstalk. Okay, so you have cables, so you're going to have crosstalk between those, and that can be a source of uncertainty. Flexing cables. That's very important for the cables inside the positioners, because when you flex a cable, you change the impedance of that cable, and that's going to change some properties. That's definitely something that is difficult to like model, or so you may need to like do a series of measurements and come up with an idea for that. Multipath, so reflections from the range, normalization, non-uniform illumination, et cetera, et cetera. You come up with like a list of terms of uncertainty. And then, and this is coming from the standard as well, and it's actually coming from one of the papers on the standard by Fordham and Blaylock. You can have uncertainties for a given frequency and for a given parameter. So here we have for gain. And as I mentioned earlier, for gain, the room scattering is not that critical, especially if you have a directive antenna. Because a directive antenna is not going to illuminate the size of the chamber that much, so you're not going to have that much energy going to the sides. But if you're trying to measure a side lobe, then your room scattering potentially can be higher. In this case, this was at a very high frequency, so it's still not much of an effect. Then, you know, what type of distribution? Antenna range alignment, that's rectangular because that can happen anytime. It's difficult to think. Some other ones are more a normal distribution, like the amplitude taper. Some are U-shaped distributions. But the guide for uncertainty measurements, the GUM, will help you through choosing those. And depending on the type of distribution, you're going to have different multipliers for it and divisors there. So here is an analysis that I made for a customer. So this is actually for a customer with a taper chamber. I divided the range in like 200 megahertz, 400 megahertz, 1, 3, and 10 gigahertz. This was for gain, so gain uncertainty in this case. And I identified 1, 2, 3, 4, 5, 6, 7 contributors. So I didn't go in with 50, like Doran Hess will have done. Now, the first one, my reference antenna. Here I have to use a reference antenna. So there is, if it's a standard gain horns, about 1 gigahertz, plus minus 0.3. If it's like other antennas, dipoles, the uncertainty was a tunable dipole, so I use plus minus 0.5. It was actually plus minus 1, but you know that was their two sigma level that they gave you, so I had to divide it by 2. So here is 0.5, 0.5, and above that 0.3. Alignment, because in this particular range, they just bring their antenna and they put it on a styrofoam turntable, leave it there. They have a pair of laser crosshairs, so they know more or less how to put it there, and they leave it there. So not a very exact positioner. So we just did some simulations and came up with some numbers. based on the typical gain of their antennas. RF system uncertainty, we just went to like the data sheets and manuals from Keysight and got their values for the different frequencies for S21 at the levels that we were measuring. Basically taking into account the path loss and all the cable losses, what is the signal they're receiving, and for those levels, what is the uncertainty that the manufacturer says. Reflectivity. So we have done VSWR test. So the VSWR test was 20 dB at 200 megahertz, 32.93 at 4 gigahertz, and so on, got in the 40s at 3 and 10 gigahertz. So based on that, we have what the potential uncertainty was for those reflections levels. And then we also have amplitude taper. So we look again at the measurements that we have, and we have about 0.5. And based on that, the potential contribution was 0.24. And then we have an impedance mismatch, but in this place they were using pads. That was part of like their internal procedures to put a 3 dB path into the reference antenna and their antenna under test. So I set those to be 0. And then, you know, how far or how close was the antenna? I mean, were they putting it correctly? They were putting the device that had the antenna right on those crosshairs, but sometimes the antenna was towards the front, some towards the back. Based on the size of the quiet zone, we estimated the potential difference in path loss there. And once I have all those, I change them to linear units. Once I get them in linear units, I do the root sum square of them, and that's my combined uncertainty. And then I switch it to dB from linear units. And then once I get in linear units, I can say that will be 1 sigma, which is 65-something% confidence that you are going to be within that range. So we went ahead and do a 2 sigma and a 3 sigma. 2 sigma is 95% confidence. That's what most labs are going to give you. 3 sigma, some national labs give you that because it's like 99% confidence. That I personally don't think is necessary. 2 sigma, 95.5-something%, that's most of the time. If I have 95.5% possibility of getting the lottery, I will be really, really happy. And basically that gives me what my, you know, uncertainty is for, you know, gain measurements. And indeed, at the lowest frequency, the biggest contributor is the reflectivity in the range and, you know, my reference antenna. Those are the biggest contributors in most cases. And then, you know, as I go higher in frequency, my room gets better. Also, my contribution from the standard gain antenna gets also a little better, and I have much better confidence. But like I said, it's a good thing to do, uncertainty analysis. I mean, you should do them also, but it helps you understanding what you're doing, and it helps you understanding what are the key issues. And then if you know which the key issues are, you can try to be better at minimizing them. You know, if it happened that here positioning of the antenna was a critical factor, then, you know, you can get a better positioning equipment to make sure that you reduce that. So, conclusions. Understand what you're trying to measure. That's I think, one of the first thing that you need to learn. Try to understand what you're trying to measure, what uncertainty levels you can leave, because that will help you. If you're understanding what you're trying to measure, it will help you select the range. And there you can save a lot of money by making the right decisions in range selection. And spend time on doing an uncertainty analysis. It doesn't have to be rigorous. Remember, that's an oxymoron. It doesn't have to be rigorous. You don't have to spend days and days. I mean, That uncertainty analysis, I think, at most was maybe like 3 days of work. The biggest time was like doing some of the method of moment simulations of misaligning things to like see what the error was. The rest of them were like quick calculations and then going through like Keysight. Finding the right Keysight manual was probably what took the longest time because Keysight didn't make the model that the customer had anymore. So I had to like come through it and eventually they found it at their place because they didn't know where they have it. And they gave me the values. But that's it. Hopefully you learned something so we can have questions now.
Yeah. Probably I already know the answer, but I just want to hear your comment. So what would be a good quiet zone value? I mean, coming back to this minus 50 request, what should be then an accurate one?
So minus 40, to me minus 40 is a more than adequate value for most side lobes that you will find even in a high gain antenna. Again, it depends on the accuracy that you want on some of those things. Let's say that you were testing one of those weather antennas and you were doing the radome on, radome off. And there you want probably to have a little more accurate, especially military radomes, a little more accurate on, okay, what is the effect of putting that radome? So you want to minimize what the uncertainty on that side lobe is. So in those cases, I may push for the minus 50 reflectivity. But in most cases, minus 40 is more than okay. For fairly omnidirectional antennas, sometimes minus 25 is more than enough. For the type of testing that they're doing, wireless testing and over-the-air testing, I think minus 25 is more than adequate for those things. So again, it's going to depend on what you're looking for. And in some cases, when you go to some special hardware in loop type chambers for some specific seekers and things like that, then you want to make sure that you have really good, like you aim to try to get minus 55 if possible. And it's difficult to measure, indeed. That's the reason that you don't go and promise minus 60 because trying to measure that is extremely difficult.
Thank you.
But in this case, quiet zone for far field measurement, right? Do you need it for near field?
For near field, you don't have per se a quiet zone. Now, you want to have a reduced reflections because those will affect your measurement. But typically in near field, if you have reflected energy in the minus 40 dB, typically it's okay. When you do the transform, it helps you in minimizing some of those effects. And then you have some numerical techniques to try to take out some of those effects from the reflected energy. But the places where you are concerned, for example, in planar near field ranges, is on making sure that you don't get standing waves between the back wall and the antenna, because then you may be scanning on one of those peaks, and it may cause an error there. Especially measuring gain, because then your gain horn may create a different slight standing wave, and then suddenly your power receive is quite different between those two. So you still have to be aware of the absorber, and in some spherical ones as well. But there, some of the numerical post-processing techniques that are available can help you a little bit on minimizing those. But like I said, minus 40 dB for large antennas, spherical near field is more than adequate. We have done those ranges with minus 30, and we were able to get good results. Once you get less than minus 30, I have seen some results for a spherical near field where they insisted on building the chamber themselves. Just remember that. You don't go and you buy a scalpel and you perform surgery on yourself. Let professionals do it. But this customer insisted on doing the chamber themselves, and they made it too short. And they have very high reflectivity from the top. And unfortunately, at the lowest frequency, the antenna was too large to be able to like reposition it within the minimum radiating sphere to be able to like use some of these processing techniques to reduce the absorber. So they have errors, significant errors at the lowest frequencies. But again, that chamber was not properly designed. So better than -30, okay. -40 for sure you're fine on spherical near fields.
And you said about if it's necessary to shield or not. When we look for a chamber, it's very easy to quote or to specify a chamber one, a shielded one, chamber shielded. But if it's not necessary to be a shielded one, how to put the requirements?
You
Because
can
you
measure,
have
you can put there that you want, if possible, to get an isolation of certain number of dBs between the inside and the outside. That's not shielding, that's an isolation from the absorber at a given frequency. And the method for measuring that will be basically based still on the 299 standard, and you will basically measure your two antennas and then place one inside and one outside to ensure that you have that attenuation. But you will measure only at the frequencies of interest of that antenna, just to make sure that that absorber has the right attenuation. But you have to make sure prior to that you're going to be okay in that you're not going to be having too high power, that you are not, that your signals outside cannot be picked up by somebody trying to like find out which frequencies, modulations, etc. you're using. So, but typically you can save a lot of money by staying away from shielding.
Yeah, but I mean the box itself, to be concrete, wood.
Oh yeah, we have built them out of from an office, a small portable office supplier. In India, the ISRO in Ahmedabad, most of the rooms were just concrete, and they will put foil on the walls and then just glue the absorber on top.
But you need to put foil.
No, you don't need to put foil. Let me rephrase that. If your absorber is over a wavelength in size at the lowest frequency of interest, then typically, whether you have foil or not behind, the performance of the absorber is going to be almost similar. When you have electrically shorter absorber, what happens is that the reflected signal from the bottom of the absorber has a different phase depending if there is no material behind or there is foil. Mm-hmm. And that phase difference that helps you with cancellation, what can do is that where you may have a null, that null shifts in frequency. And suddenly you may end up actually that without foil behind, you have better performance at a given frequency, but then your peak has moved to a frequency where you're expecting maybe a lower value and now it has a higher value. But that only happens, like I said, when the absorber is smaller than one wavelength in thickness. If it's larger than one wavelength, and definitely two wavelengths, you can simulate it with and without foil behind, and you don't see a measurable difference.
And can I go, for example, that company that built Frigo?
Yeah. One of, like I said, we use, when we do unshielded rooms, we go to a smaller company that what they do, they make portable offices. So to having a factory floor, they will have these insulated offices. It's a wall that is about probably close to 10 centimeters thick, that is full of foam, and is very thin aluminum clad, and it's easy to install, and it has regular doors, and we have built several of those ranges. And in Europe, I know that some of my competitors, they actually go to a company that makes freezers for like meat, and they just build them, and they just glue the absorber inside.
Because
And
it-
they you know,
because
work okay.
it need to stand the weight of the absorbers.
yeah, you just need to make sure that you know, the wall can, but the absorber, although it can be potentially heavy, is not that heavy. Those structures typically can support it. At least the many ones that we have built, I haven't heard of any of them falling down. So.
Probably the door is a problem, if the size of the door.
We use typically standard double doors, and you know, we haven't had an issue.
3 by
Yeah.
3.
Hmm?
If the door is 3 by 3 meter,
If it's larger than that, then we basically, they hire a separate company to make the door for them, and they just have the door on a separate frame that attaches to like their thing. But it's still cheaper than a shielded door.
Just a question. I liked very much that you mentioned the Benoit Dera article. Earlier this year, we found these articles, and we were able to measure some things that we couldn't without this knowledge. But even though I'm doing peak power measurements, but I have to guarantee no reflections of the floor, because it's a semi-anechoic chamber. So I have to put some absorbers on the floor.
Yep.
Is there a width, particular width that I have to fulfill with these absorbers and on the floor, or?
So there is a set of equations. I'm trying to remember if they're in my book. If not, I can find them for you. They were definitely on the blue book, the All Scientific Atlanta Blue Book, which you can download for free from the NSI-MI website. And Bill, can you find the link for the literature or the library that we have in our website, and then later on show it to him? So Bill is going to find it, but there you can download the blue book on antenna microwave. And for outdoor ranges and outdoor reflective ranges, there was a calculation of Fresnel zones to cover the floor. And like I said, there's 3 equations, and they tell you how long, how wide. It's basically an ellipse, but basically just look at long, wide. And the frequency, the height of the antennas.
I used the fourth zone, the fourth Fresnel zone.
Yeah, 4 Fresnel zones. Even 3 Fresnel zones, I think, most cases is more than adequate. They used to claim 6, but I know a lot of the anechoic chambers that I have designed in my life, I have used like 4 or 3 for the specular treatment, and they pass, you know, the specifications with no problem. So yeah, that's the way of like estimating that.
Okay, thank you.
Okay, so well, do you have those papers? Where can we put them? Tell you what, this And I guess that's it. Well, thank you, everybody, for coming, and, we'll see you next time we organize something.